let's understand basics of friction through examples, through illustrations, starting from very simple. Let's keep building up, right? To begin with, I have one very simple situation at your disposal. We have a body of mass 10 kgs resting on a surface that has friction. And the coefficient of friction, this is a horizontal surface, and the coefficient of static friction between the two is 0.2 and the coefficient of kinetic friction is 0.15. So now there are a few basic computations that we want to have in this context. One, the first part, we want to obtain the maximum static friction between the two surfaces. Now how does one obtain maximum static friction? Maximum static friction is mu times n. So I would have to compute the normal reaction between the two surfaces, right? The body, if I have to draw the free body, there is m 10 kgs, so 100 newtons acting like this, and there is normal reaction r from the ground acting this way, right? And there is of course a horizontal force F that is given this way. Now, what's the value of r? Since there is no vertical acceleration, r must be just about 100 newtons. So r must be 100 newtons, which is the normal reaction between the two surfaces, right? So the first part of the problem, maximum static friction between the two, Fs max, is going to be mu s times coefficient of static friction times the normal reaction r. What's the coefficient of static friction? Coefficient of static friction is 0.2. So this is like a 0.2 into 100 that newtons, that makes it 20 newtons, right? Now what does it mean? It means that the maximum holding force that can exist between these two surfaces is to the extent of 20 newtons, right? So if you apply a force F which is less than 20 newtons, then the frictional force will be equal to F itself, right? So as long as capital F is less than or equal to Fs max or 20 newtons, right? So first of all, this body has a tendency to move to the right, so frictional force F will act on it to the left, And what's the maximum possible value of F? The maximum possible value of F is 20 newtons under static conditions between the two surfaces, right? So then, when capital F is less than or equal to 20 newtons, frictional force just about balances capital F. That's the rule of friction. That's the basics of friction, right? That means, so if I apply a force 5 newtons, small f will be 5 newtons. When I apply a force capital F equal to 10 newtons, small f will be 10 newtons. 11 newtons, this will be 11 newtons. 15 newtons, this will be 15 newtons, and so on and so forth. But friction will keep balancing capital F. Friction will keep balancing capital F as long as capital F does not exceed 20 newtons. 20 newtons is the maximum static friction. That means the greatest value of small f under static conditions is 20 newtons. That means up to capital F equal to 20 newtons, friction will keep matching the value of capital F. Friction will keep matching the value of capital F. That's what happens. So if I apply a force F equal to 15 newtons, when F is 15 newtons, this 15 newtons is less than maximum static friction. Frictional force can be to the tune of 15 newtons, so small f turns out to be 15 newtons, right? When capital F is 20 newtons, then also friction force can oblige. Frictional force will still be 20 newtons. So when capital F is 20 newtons, frictional force will still be 20 newtons. But the moment this capital F exceeds 20 newtons, there would be relative motion between the two surfaces. This will begin to slide over this. So for example, when F becomes 21 newtons, right, frictional force cannot match 21 newtons. Relative motion between the two commences, and frictional force will no longer maintain this in equilibrium, cannot prevent relative sliding. Frictional force cannot prevent relative sliding. What happens is relative motion commences, and now frictional force changes character. From static it will become kinetic. And kinetic friction, the kinetic friction is one single value of friction that exists between the two surfaces when there is relative motion between them, and that's going to be coefficient of kinetic friction into normal reaction R. Kinetic friction mu k is 0.15, so this is like 0.15 into normal reaction R. Normal reaction R is how much? 100 newtons. 100 newtons. So this becomes 15 newtons. So then once relative motion starts between the two surfaces, the value of the frictional force becomes kinetic and equal to 15 newtons. That means when capital F is 21 newtons, very clearly anything beyond 20 newtons, there would be commencement of relative motion. Frictional force will then become kinetic, will no longer be static, and will then become 15 newtons. Frictional force will then become 15 newtons. And there would be acceleration. What would be the acceleration of this body then? It's going to be the net force, which is 6 newtons, divided by the mass. Mass of this is 10 kgs, divided by 10 meters per second squared. That is 0.6 meters per second squared. Yes or no? Right? So there were two important things that you needed to know for the common surface. One, static conditions will be maintained only up to a certain point, right? And the maximum frictional force for static conditions that could exist between the two is maximum static friction, which is mu s times the normal reaction, which turns out to be 20 newtons. So if you apply a force 5 newtons, 6 newtons, 7 newtons, up to 20 newtons, frictional force will just about balance capital F, but beyond that point it will give in. If you apply a force F equal to 21 newtons or 20.5 newtons, relative motion will start. And then friction will change its character. From static, it will become kinetic. And then value of kinetic friction will be a constant. Static friction keeps varying up to a certain point where it reaches its maximum value, but kinetic friction, when there is actual relative motion between the two, friction force has just one value, which is kinetic friction, in this case 15 newtons. So then there would be acceleration. Right? So this was the first in the list of very simple things that you needed to know on friction. Let me add a little more to it. In the meantime, thank you so much. We'll catch you in a little while. Bye-bye. Again, setting your foundation right. Another illustration which will help you comprehend things a little better. So we have a fixed horizontal surface, and there is a block of mass 20 kgs resting on this fixed horizontal surface, and a 100 Newton force is applied as shown, right? And coefficient of static friction between the body and the surface is 0.5. That means at this interface, coefficient of static friction is 0.5. Now there are two cases. One, when this surface is fixed. Two, when this surface has an upward acceleration of 2 meters per second squared. In both cases, I want to find the maximum static friction. I want to be able to find maximum static friction. Now what do? All right. If I have to draw the free body diagram, let's say in this case, what are the forces? There is 200 newtons because of the weight. There is normal reaction R from the ground to maintain it in vertical equilibrium. And maximum static friction would be mu s times R. This 100 Newton force could be resolved as 100 cos 37 degrees. Cos 37 degrees is 4 by 5. So this will become like 80 newtons. So I hope you remember these values. Cos 37 degrees is 4 by 5. Sin 37 degrees is 3 by 5. Right? And then a vertical 100 sine 37 degrees, which is 60 newtons. Now I want to find maximum static friction. So for maximum static friction, Fs max in this case is simply going to be mu s times the normal reaction R. Mu s times the normal reaction R. And how does one compute the normal reaction? By writing its equation of motion in the vertical direction. No acceleration in the vertical direction would mean R plus 60 newtons must balance 200 newtons, the weight. That means R must be 140 newtons, right? And once I have R in place, Fs max can be obtained as 0.5 times R, which is 140 newtons. That makes it 70 newtons, right? That's one. The second one is when everything remaining the same, but this fellow having an upward acceleration of 2 meters per second squared. Once again, there is, okay, let me call it 20 kg itself so that calculations become similar, right? We can compare similar situations. So there is 20 kgs, 200 newtons acting downwards because of Mother Earth. This is the new normal reaction between the two. And the net of all of this is an upward acceleration of 2 meters per second squared. So if I apply Newton's second law to this, then what do I get? 60 plus r minus 200 is the net upward force. And that must be equal to mass of this, which is 20 into acceleration 2 meters per second squared. Right? So that gives me r equal to 240 minus 60, that makes it 180 newtons. So then again, the maximum static friction in this case is going to be Fs max is going to be mu s times r. Mu s is 0.5 into r, which is 180 newtons. So that makes it 90 newtons is the maximum static friction. 140 newtons is the maximum static friction here, whereas 90 newtons is the maximum static friction there, right? So I'm sorry, 70 newtons is the maximum static friction here, whereas 90 newtons is the maximum static friction here. Now the important thing is, between this and this, what has increased? The normal reaction has increased, so that this could have had an upward acceleration. That is why maximum static friction increased. Yes or no? Alright, I'll add more to it. In the meantime, thank you so much. Bye. Another very direct situation, and you must be familiar with this. We have a fixed inclined plane, and there is a body of mass m resting on the surface. The surface has coefficient of static friction mu s. Between small m and the inclined plane, the coefficient of static friction is mu s. We want to find the value of theta, or the range of theta for which slipping would just start, right? That is what we need to find. So we need to find the value of maximum static friction. And in order to find the value of maximum static friction, we need to know the normal reaction between the two. Now realize that there is mg acting downwards. This is the normal direction. The normal obviously makes an angle theta with the vertical. This is mg cos theta. This is mg sin theta. Right? These are components of it, and there is normal reaction n like this, and there is no vertical acceleration in this direction. Therefore, n is mg cos theta. So we know the normal reaction, which is mg cos theta. And once we know n is mg cos theta, then we know maximum static friction. Fs max, maximum static friction, is going to be mu s times n. Mu s times n means mu s times mg cos theta. That's maximum static friction. Now, it has a tendency to move down, so friction will act in the upward direction F. Right? Yes or no? And for equilibrium, F must be just mg sin theta, right? If theta goes on increasing, as theta increases, realize that as theta increases, mg sin theta will increase. And it will have greater and greater propensity to slide down, right? But at what point will it start to slide? At a point where mg sin theta just about exceeds maximum static friction mu s times n, just about exceeds mu s times n. That's the maximum static friction, right? Because static friction is holding the two surfaces. Mg sin theta is trying to cause sliding, right? So if mg sin theta just about is able to manage maximum static friction, sliding will commence. So this is when sliding will just about commence. That means sliding will commence when mg sin theta is greater than or equal to mu s times n. N is mg cos theta. That means tan theta must be greater than or equal to mu s. Tan theta must be greater than or equal to mu s. That means the minimum value of theta that will cause it to slide would be a theta for which tan theta is mu s. That's the minimum value of theta. Any value of theta such that tan theta is larger than mu s will cause it to slide. That means if you have a plane horizontal, if you have a plane at a small angle theta, And this is the particle m. For small values of theta, tan theta will be less than mu s and they won't be sliding. But as you go on increasing the inclination, tan theta becomes larger and larger and larger. At some point, tan theta just about becomes equal to mu s. When tan theta just about becomes equal to mu s, friction reaches its maximum possible value under static conditions, which is maximum static friction. Now, if theta increases more than that, then the value of mg sine theta is good enough for it to overcome friction and to cause commencement of sliding. That means when mg sine theta just about exceeds maximum static friction, that means theta is such that tan theta greater than mu s, sliding will start. That means when theta is greater than or equal to tan inverse mu s, sliding will start. At theta equal to mu s, friction reaches its maximum static value, which is mu mg cos theta. Yes or no? So this was another simple situation, and I hope you are comfortable. You must remember this. If there is a fixed inclined plane, then the limiting value of theta for which sliding just about starts is given by tan theta equal to mu s. I obtain a certain value of theta from this. If I exceed theta beyond this value, then sliding will start, because then mg sine theta will become larger than maximum static friction and there would be acceleration down the plane. Yes or no? This much for this time. More very shortly. Bye-bye. We are beginning to learn more and more things about friction. We've just got started with very direct basic applications of friction in context of some, again, very downright rudimentary applications on friction. I have two more situations. This is situation A, and there is a block of mass m resting on a surface with coefficient of friction mu, and I apply a pulling force P like this. So this is a pulling force. Right? I apply a pulling force P like this at an angle alpha with the horizontal. For a given alpha, what must be the smallest value of P for which sliding will just about occur? So that's this situation. Let's see what to do with this. Very clearly, P could have been resolved as P cos alpha horizontally and P sin alpha vertically, right? And the other forces acting on this are like mg downwards and normal reaction r from the ground upwards, right? And we are assuming that P sin alpha does not exceed mg. Which means it maintains contact with the ground. I'm assuming contact is not lost. So then for vertical equilibrium, if I have to calculate the value of r, then what does r turn out to be? R plus P sin alpha to be able to balance mg. That means I know the value of r. The normal reaction between the two is mg minus P sin alpha. Right? And what is maximum static friction between the two surfaces? In this case, see, P cos alpha is trying to pull it to the right. Frictional force will act on it to the left, but only to a maximum value. This F will have a maximum value, which is Fs max, which is like a mu s times the normal reaction R, which is mu s into mg minus P sin alpha. Right? Now, in order that sliding just about happens, this horizontal force must just about exceed maximum static friction. Yes or no? In order that sliding just about happens, when it's for sliding, P cos alpha must be just about greater than or equal to maximum static friction. That means P cos alpha, this must be greater than the maximum possible value of F. P cos alpha must be greater than or equal to F max. F max is this, which is like mu s into mg minus P sin alpha, right? So then I transpose the whole thing on the left hand side. So P into cos alpha plus mu s sin alpha greater than or equal to mu s mg. So then I get P greater than or equal to mu s mg divided by cos alpha plus mu s sin alpha, right? That means the minimum value of P acting at an angle alpha with the horizontal for which sliding happens is this value. If I apply a value of P just larger than this, sliding will take place. For a value of P just about equal to this frictional force will get to its limiting value, which is maximum static friction, right? So now we have, so this was a pulling situation. There is a force P which could be pushing a block this way, right? And if it's pushing a block this way, I want to find the minimum value of P for which sliding happens, right? Again, resolve P as P cos alpha horizontally and P sin alpha vertically, right? There is normal reaction R from the ground, and there is mg acting downwards. There is mg acting downwards, right? So I can obtain R and therefore maximum static friction. Very clearly for vertical equilibrium, you can see that R must balance all the downward forces mg plus P sin alpha, right? Maximum static friction in this case is going to be mu s into R. See, now you're trying to push. This is a pushing force. It will try to cause this body to slide to the right. Therefore, very clearly, friction will act on it to the left. But the maximum F is going to be maximum static friction. The maximum value of the frictional force is going to be maximum static friction, right? So, and whose value is going to be mu s into R. So, Fs max. F max, maximum value of this is maximum static friction, which is mu s into R, which is like mu s into mg plus P sin alpha, right? And in order that this could just about move, P cos alpha must just about be larger than maximum static friction. That means P cos alpha must be greater than or equal to mu s into mg plus P sin alpha. That means if I transpose to solve for P, cos alpha minus mu s sin alpha must be greater than or equal to mu s mg, which means P must be greater than or equal to mu s mg divided by cos alpha minus mu s sin alpha. This is what happens. That means the minimum value of P for which pushing will cause it to slide is mu s mg by cos alpha minus mu s sin alpha. That is what happens, right? So we have again two very standard routine situations that we've dealt with: pushing and pulling, and the minimum force that will cause it to slide over the surface. I hope you're comfortable with this, but we still have a long journey to go even in terms of the bare minimalistic framework. In a short while, I'll catch you with some more very simple stuff. Once again, with a situation, an inclined plane kind of a situation. There is a body of mass m resting on a surface, inclined plane, inclined at an angle theta with the horizontal, and mu s is the coefficient of static friction between the body and the plane, right? And suppose mg sin theta is more than maximum static friction between the two, and it has a tendency to slide downwards. It has a tendency to slide downwards. So friction will act upwards. Friction will act upwards, and if mg sin theta is more than maximum static friction, it will actually have a tendency to slide down. Now, if it has a tendency to slide down, friction force will act on it upwards. But if mg sin theta is more than maximum static friction, then it'll overcome static friction and it'll slide down. Now what I do is, so very clearly friction will then act upwards. Now, I bring in another force, external force P, acting at an angle alpha with the plane. Acting at an angle alpha with the plane. I want to find the minimum value of P. I want to find the minimum value of P acting at a certain fixed angle alpha for which this will not slide downwards. Sliding downwards could be prevented. Yes or no, right? Very clearly, why am I trying to do that? Mg sin theta is more than maximum static friction, so it will slide down. So very clearly, to counter mg sin theta, I apply a force P at an angle alpha, and what should be the smallest value of P so that I can prevent it from sliding downwards. Yes or no, right? In fact, what we need to do here is, since mg sine theta is capable enough of causing this body to slide, that means if there was no P, this F would have become maximum static friction anyways, Now, what's the value of maximum static friction when a force P is applied? F then would be mu s times n, normal reaction, mu s times n, the normal reaction between the two surfaces. So, maximum static friction between the two, F max is going to be mu s times n. And how does one compute n? From equilibrium in this direction. We have n plus p sine alpha, just about balancing mg cos theta, right? So if P is just about preventing this from sliding, then this F would have just about become maximum static friction and there is equilibrium. It's precariously in equilibrium, where the component of P in this direction, the frictional force which would have reached its maximum possible value, which is maximum static friction, is just about balancing mg sine theta. That is what must have happened. So that's a limiting value of P, right? That's the smallest value of P for which sliding could be prevented. So then, what I do here is I know the value of n plus p sine alpha is mg cos theta. So I know n as mg cos theta minus p sine alpha, as you can see, right? And p cos alpha. In a limiting case, p cos alpha plus this force which would have become maximum static, small f, which would have acquired a value mu s times n. So mu s times n is this, which is mg cos theta minus p sine alpha, right? That must just about balance mg sine theta to prevent slipping or sliding down, right? So I can obtain the value of p from this. So I have like a p into cos alpha minus mu s sine alpha, just about becoming, I take this transpose terms, sine theta minus mu s cos theta, right? So the least value of P is going to be mg into sine theta minus mu s cos theta, the entire thing divided by cos alpha minus mu s sine alpha. This is what happens, right? So if I apply a value of P equal to this F will just about become maximum static friction, and P cos alpha plus the maximum static friction would just about counter mg sine theta, holding it precariously in a state of equilibrium parallel to the plane. Yes or no? Thank you so much. Bye-bye, but more to come. Another very simple situation related to friction. There is a block of mass m resting on a rough surface, and coefficient of friction being mu between the body and the surface. There is a force F which is applied at an angle theta at an angle 30 degrees with the horizontal, and this moves with constant velocity. The mass then moves with constant velocity. It's given that the value of F is 1.5 times the weight of the block, right? We want to be able to calculate the coefficient of friction. Now, one thing, if it's moving with constant velocity, what does that mean? It means summation of all the forces must be 0. Acceleration is 0, right? Acceleration is 0 means no net force acting in any direction. That means now F cos 30 degrees acting this way must just about balance. See, since there is relative motion between the two, so what if it's moving at constant velocity? There is velocity and there is relative motion between the two. So the frictional force would have reached its limiting value, which is mu times n, right? Because there is actual rubbing between the two surfaces, and F cos 30 degrees must just about balance n. So F cos 30 degrees just about balances mu times n, so that there is no net acceleration and it could have moved with constant velocity. But what about n? How does one compute n? Very clearly, n must take care of mg plus f sine 30 degrees. So n must take care of mg plus f sine 30 degrees. F is given to be 1.5 times mg. So mg plus 1.5 mg, and sine 30 degrees is half. So 0.75. So that's 1.75 mg. That's n, right? So f cos 30 degrees is mu times n. N is 1.75 mg. What about F? F is given to be 1.5 mg. So 1.5 mg, and cos 30 degrees is root 3 by 2. So mg will get cancelled, and there we have the value of mu. Mu is 1.5 root 3 divided by 2 into 1.75 means 3.5. So which is 3 by 7 root 3. That's the value of mu. That's the value of mu. Now whatever this turns out to be, right? You can plug in root 3 as 1.732. So another very simple situation. Constant velocity means frictional forces must be exactly countered by F cos 30 degrees so that there is no acceleration. Yes or no? Thanks. Bye-bye. Let's look at another situation which will again, further ensconce ideas on friction for you. We have a block of mass capital M resting on a smooth horizontal surface. There is another block of mass small m on the vertical face of capital M, and the coefficient of friction between small m and this vertical surface is given to be mu s. We want to be able to find capital F. We want to be able to find capital F so that there is no relative motion between small m and capital M. Now, very clearly, what would capital F do to capital M? It will cause capital M to move to the right with an acceleration a, right? And if there is no relative motion between small m and capital M, small m should share a common acceleration a with capital M, right? If the acceleration of capital M is a to the right, acceleration of small m should also be small a to the right, so that there is no relative motion between the two. That is what must happen. Now, what really transpires is, I can find a from these considerations. If I draw the free body diagram of capital F plus small m, capital M plus small m, capital M plus small m in the horizontal direction, there is only one external force, right? The normal reaction between small m and capital M was an internal force when I look at capital M plus small m together, right? So that will not feature in this. So then, should I not have a capital F equal to capital M plus small m into a, right? The common acceleration. So a then turns out to be capital F by capital M plus small m, right? Now once I have a, let me go to small m. What causes small m to have an acceleration a to the right? Okay, free body diagram of small m, there is mg downwards. Capital M will exert on small m a normal reaction n like this, right? Yes or no? And that is going to cause it to have an acceleration a to the right. By the way, in the vertical direction, mg has to be balanced. Mg has to be balanced, and what would balance mg? There is going to be frictional force F that must balance mg. That must balance mg. Yes or no? So then, n must be small m into a. And we know the normal reaction must be small m into a, which is m into F by capital M plus small m, right? Now what does friction do? Friction must just about balance mg. Friction must just about balance mg. So if friction just about balances mg, that means this friction should be less than or equal to maximum static friction, which is mu s into n, right? That means mg must be just about less than or equal to mu s, right? Isn't it? This frictional force F must be mg. Small f cannot exceed maximum static friction, mu s into n. So mg must be less than or equal to maximum static friction. So mu s into n, what is n? N very clearly is mf by capital M. Mf by, from this, capital M plus small m, right? So that gives me F greater than or equal to, so the small m will get cancelled, G into capital M plus small m divided by mu s. So the minimum value of F that will prevent relative motion between the two, F minimum that will prevent relative motion between the two, is going to be G by mu s into capital M plus small m. Yes or no? Right? That is how it happens. That is how it happens. But we are still not done with rudiments. There are more illustrations on rudiments that will see us sail past things more effectively. But I hope you are all comfortable with things that I've been doing so far. This much for this problem, but more to come. Thanks a lot. Bye-bye. For your eyes only, let's look at another problem on friction. So this time we have two blocks and they're connected by means of a light inextensible string passing over a fixed pulley. And this 10 kg block is on the horizontal and the coefficient of friction, both static and kinetic, between the two surfaces is 0.4. And this is not in contact with any surface. This is solely moving under the influence of gravity and tension because of the string. What we want to do here is analyze this motion. Okay, so I want to find, let's say, the displacement of the block in 2 seconds. I want to find the displacement of the block in 4 seconds. Given that this is t equal to 0, s is 0, right? I want to find where the block is 2 seconds later. I want to find where the block is 4 seconds later. These are things that I want to obtain here. So at this instant, at the instant shown, which is referred to as time t equal to 0, the velocity of the block is 12 meters per second. So if this is moving leftwards with 12 meters per second, then from string considerations, this is moving up with a velocity of 12 meters per second. And realize that there is mg on this 10 kg block. On this 10 kg block, there is mg, which is 100 newtons acting downwards, and normal reaction r from this horizontal surface acting upwards to keep it in equilibrium. So r must be 100 newtons, right? And since this is moving to the left with a velocity v, friction will act to the right and would be kinetic in character because there is actual rubbing between the two surfaces. So that's going to be mu k times r. That's going to be the frictional force. And what is mu k times r? So frictional force acting to the right is going to be mu k times r. Mu k is given to be 0.4. So 0.4 times 100, that makes it 40 newtons. 40 newtons frictional force is acting in this direction. So when it's moving leftwards, there is a frictional force F equal to 40 newtons acting to the right? There is tension T acting like this. Yes or no? That's a free body diagram of this. And of course, there is mg and normal reaction from the ground, which I am not showing here because it will add to clutter. And there is 50 newtons because of Mother Earth acting on this 5 kg block, and there is T like this, right? Very clearly, it's moving to the left, but all the forces acting on it are to the right. So there is a rightward acceleration that it has, right? This rightward acceleration, suppose, is A. If this has a rightward acceleration, this will have a downward acceleration. Yes, so although it's moving upwards, it has a downward acceleration, means it's retarding. This is moving to the left, but it has a rightward acceleration, means this is also retarding. That is what is happening, right? So in any case, A is the value of acceleration of this in this direction and this in this direction. So writing equations of motion for this, what does it turn out to be? T equal to 10A, right? I'm sorry, T plus the frictional force 40 newtons. That must be equal to 10 into A. That's equation 1, right? What about this? 50 newtons minus T equal to 5A, right? Equal to 5A. 50 minus T is 5A. That's equation 2. So I'll be able to obtain the value of A from this. If I add these two, then I have 15A equal to 90. 15A equal to 90, or A equal to 6 meters per second square. That's the acceleration. Realize that friction is in the same direction as acceleration. In fact, the moral of the story is friction is not opposed to relative acceleration, it's opposed to relative velocity. Realize that this fellow has a leftward velocity, though a rightward acceleration. It has a leftward velocity but a rightward acceleration, and friction is supporting the acceleration. Why? Because if friction acts in this direction, it will oppose the relative velocity between the body and the surface, which is 12 meters per second. So rule of the game, moral of the story, the cardinality is that friction will oppose relative motion but not relative acceleration, right? So good for us. Now this is what happens. 6 meters per second squared. So it has a leftward acceleration of 6 meters per second squared. This has a downward acceleration of 6 meters per second squared. And so this is retarded. This is retarded. would you want to believe that after a while its velocity will become 0? It'll keep moving to the left. Its acceleration would be 6 meters per second squared, but it'll keep moving to the left. And after a while, its velocity is going to become 0. Its velocity is going to become 0. So t seconds from this instant, its velocity is going to become 0. Let's see when. When exactly the velocity becomes 0. When exactly the velocity becomes 0. So, this guy has a velocity of 12 meters per second and has an acceleration in the leftward direction of 6 meters per second squared. After a while, its velocity will become 0. Let's say at an instant of time t0, its velocity will become 0. Can I find t0? Right? This is the instant of t0, time t0, when its velocity is rendered 0. So I apply v equal to u plus at, 0 equal to u, which is 12, a in this direction, so minus 6 into t0, right? V equal to, I have taken leftward positive, so velocity becomes 0, is initial velocity 12 minus at, right? So t0 then becomes 2 seconds. So 2 seconds from this instant, its velocity will become 0. And when its velocity becomes 0, it would have acquired a certain displacement in the leftward direction, S0. How does one compute S0? S0 until this instant of time. So this would have moved S0 to the left, this would have moved S0 upwards because of string considerations. S0 would be initial velocity 12, ut plus half at squared is what I'm going to apply. 12 into t0, which is 2, plus half of a, which is now minus 6, into t0 squared, which is 4. Ut plus half at squared. So what does this turn out to be? 24 minus 12, which is 12 meters. 12 meters is its leftward displacement. So at t equal to 2 seconds, what happens? The velocity of this becomes 0. Velocity of this becomes 0. And the leftward displacement acquired is 12 meters, right? This is what has happened in 2 seconds, right? Now, beyond this point, it would be an interesting situation to explore. Let's see what happens beyond this point. So, can I just remove the clutter and redraw the figure? So, when I redraw the figure, starting from this point, so its velocity has become 0. I've done some computations here, and I'm going to remove all of it for the time being, so that there is no clutter. So, things that have happened so far. Things that have happened so far. At t equal to 0, it started here, moving with the velocity 12 meters per second. At t equal to 2 seconds, its velocity would have become 0. At t not equal to 2 seconds, its velocity would have become 0, right? And so let me just connect the string. If I connect the string, I have something like this, right? Its velocity has become 0. Okay. Now what is going to happen? Now what is going to happen? Hey, once its velocity has become 0, it's a new system that we have to deal with. What's that new system? There is a 5 kg block here. The velocity of this would have also become 0 because these guys are connected by a string at all times. The velocities of these two must be the same, right? Speeds must be the same. This is the 10 kg block. This is the 10 kg block. This is also at rest, right? Would you not want to believe that if this has come to rest, it would now want to move down? It would now want to move down, right? If this wants to move down, this wants to move to the right, right? So if this moves down now with an acceleration a0, this will move to the right with an acceleration a0. That's string considerations. That's string considerations, right? Now, I'm assuming they actually move, right? I've computed maximum static friction between the two. We've done that is 40 newtons. That is not going to change. That's a basic character. That's a basic character. 0.4 into 10 into 10, that's 40 newtons, right? There is tension acting this way. And if it has a tendency to move to the right, frictional force will act on it to the left. And we are assuming T is good enough to begin with. Let's assume that T is good enough for this to move to the right. T overcomes maximum static friction. That means there is actual relative motion between the 10 kg block and the ground, right? So if there is actual relative motion between the 10 kg block and the ground, then the force of friction would have reached its maximum value of 40 newtons. 40 newtons. That's frictional force, right? Now, I want to be able to find A naught. I want to be able to find A naught. And of course, you know, if this is S equal to 0, this is S equal to, I think we have computed this as 12 meters, right? This being the origin, let's say. Now let's obtain A naught, because we are expecting this to move down and we are expecting this to move to the right, right? So what's the equation of motion for this? T must be 10 into A naught. That's one. What's the equation of motion for this? 50 minus T must be 5 A naught. That's 2. Yes or no? Oh, there is one more force. Sorry. There is T minus 40. T minus 40. So I must say T minus 40 because there is friction. I somehow happened to miss this. T minus 40 must be 10 into A naught. Right? This gives us an opportunity to obtain A naught. How? Let me add the two. So I get like a 15 A naught equal to 10, or A naught equal to 2/3 meters per second squared. 2/3 meters per second squared is the acceleration. So this moves to the right with an acceleration of 2/3 meters per second squared. This moves down with an acceleration of 2/3 meters per second squared. Now, this was t equal to 2 seconds. Now, 2 seconds beyond this point would be 4 seconds, right? So we wanted to know what happened at t equal to 4 seconds. That means 2 seconds from this instant. 2 seconds from this instant. This guy, this 10 kg block, this was s equal to 0. This was s equal to 12 meters. Now it starts with 0 velocity, right? It's come to rest momentarily, but it has a rightward acceleration which will build velocity to the right. So then it has an acceleration of 2/3 meters per second squared, right? This is this 10 kg block. Now, how much will it move to the right in 2 more seconds? That means this was t equal to 2 seconds. 2 seconds from this point, how much would it have moved to the right? It would have moved to the right by an amount x right, which is ut, u is 0, t which is 2 seconds from this instant, ut. So t, of course, half of a naught, which is 2/3 into t naught squared. T naught squared means from this point onwards 4. 2 seconds from this point, half at squared. So that makes it 4/3 meters to the right, right? That means originally it was s equal to 0, now it's s equal to 12 meters, and at t equal to 4 seconds. That means 2 seconds from this instant, it's at s equal to how much? 4/3 meter, 4/3 meter. That means what is its net displacement starting from its original point? This is its net displacement. How much is it? 12 meters, and this is 4/3 meter. This is 4/3 meter from here. 4/3 meters from this point, right? So this length is going to be 12 minus 4/3. 12 minus 4/3 meter, which is like 36, 32/3 meters. 10 2/3 meters is its displacement to the left, starting from where it was at time t equal to 4 seconds. Yes or no? Right, this much for this time, but promise to come back with a bang with some more simple examples and with increasing levels of complexity, but nothing difficult about it. So much so far. Bye-bye. Have fun. 2 more very ordinary situations, and as far as friction is concerned, we have a block of mass m equal to 10 kgs moving to the right with a speed of 5 meters per second horizontally, and coefficient of kinetic friction between the body and the surface is 0.1. So first of all, what's the nature of friction between the body and the surface? What's the nature of the friction? Obviously kinetic friction. Kinetic friction, right? And kinetic friction is easy to deal with because there is only one way you can formulate kinetic friction, which is mu k into normal reaction n. So then realize that there is mg, which is 100 newtons acting downwards, normal reaction r from the ground, and r in this case must be balancing 100 newtons. So normal reaction is 100 newtons. So we have mu k into r. R is mg. So let me just write mg. I'll tell you a specific reason why I'm writing it as mg. This is mg, r is mg, which is actually 100 newtons. So that's kinetic friction. And what's the direction of kinetic friction? Kinetic friction will oppose relative motion. It will not oppose acceleration, it will oppose relative motion. So if this is moving to the right with respect to the surface, kinetic friction will act to the left. All kinds of friction, kinetic or static, it will oppose relative motion or prospect of relative motion. So if friction acts to the left, there is obviously, this is the only horizontal force acting on it, so the acceleration will also be to the left. Acceleration is going to be Fk divided by m. Fk divided by m, as you can see, acceleration is Fk divided by m, that you can see is mu g. Mu g is the acceleration, which does not depend on m. That's why I wrote it as mu mg, so as to share with you that this acceleration which is to the left, courtesy kinetic friction, does not depend on m. And what's the value of this acceleration which is to the left? Fk by m, which is mu g. Mu is of course mu k. Mu is of course mu k in this case. So 0.1 into g, which is 1 meter per second squared, is the leftward acceleration. The particle is moving to the right. It has a leftward acceleration of 1 meter per second squared. So obviously it's retarding. It's retarding, right? Retarding. And the value of the retardation is mu g, which is opposing velocity, which is essentially opposing velocity. So obviously what would you expect? You would expect the velocity of the particle to become 0 after a while. So velocity at any given instant of time t is given by, as long as the particle is moving, is v naught minus mu gt, because it's retarding. A is mu g, right? So that gives me, when does v become 0? V becomes 0 at an instant of time t given by this. So t equal to v naught by mu g. At an instant of time v naught by mu g, the particle comes to rest. What is this? This is 5. What is mu g? Mu g is the retardation, which is 1 meter per second squared. So this is 5 seconds. So 5 seconds from this instant, the particle comes to rest, right? So this is a common situation, and you must keep a tab on this. So if there is a particle moving to the right, there is a block moving to the right with a certain velocity, there is kinetic friction acting on it to the left, and the value of the kinetic friction is going to be mu k mg. Mu k mg. Mu k times normal reaction r. R is mg to prevent vertical acceleration. And then the retardation which is to the left, the acceleration, which is to the left, opposing the velocity and therefore referred to as retardation, will always be mu g in situations like this, and therefore I can compute the time it takes for velocity to become 0. Let's look at this inclined plane. This is an inclined plane with friction, and coefficient of static friction is mu s. Coefficient of static friction is mu s, and let's say mu s is roughly equal to mu k in this situation. And if the inclined plane is fixed, we pretty much know the regime of theta for which this is going to slide down the plane. See, its weight could be resolved as mg cos theta perpendicular to the plane, mg sin theta parallel to the plane. So it has a propensity to slide down. So friction on it will act upwards, right? Now whether friction is enough to support it or not will depend on theta. Or rather, whether mg sin theta is bulky enough or not to cause it to slide will depend on theta. So for it to slide down the plane, for it to be able to slide down the plane, I have told you the following. Theta should be such that tan theta must be greater than or equal to mu s. If tan theta is greater than or equal to mu s, it's going to slide down the plane. It's going to slide down the plane, right? Now, suppose it slides down the plane, which happens obviously for theta such that tan theta greater than or equal to mu s, which means now what? So if it is actually sliding, what's the value of the frictional force? The frictional force is going to be mu s. Mu s and mu k I take roughly the same in this case. Let's say only for convenience, say mu s is roughly the same as mu k, and the frictional force acting upwards will now be kinetic friction, Fk, which would be mu k into n. N would be equal to mg cos theta to prevent acceleration perpendicular to the plane. So which is like mu k, n turns out to be mg cos theta, which means now what is the net force acting downwards in this case, the net force acting downwards, F parallel to the plane and downwards is what? Is like a mg sine theta minus Fk. Fk is mu k into mg cos theta. Mu k into mg cos theta. That's the force acting down the plane, parallel to the plane, right? And it will be sliding down and experiencing this net force parallel to the plane. And then what would its acceleration be parallel to the plane? Its acceleration parallel to the plane would be this divided by m. This divided by m. So which is like a g sine theta minus mu k cos theta. Mu k g cos theta, right? Which is like g into sine theta minus mu k cos theta. That is its acceleration parallel to the plane. Now suppose the length of the plane was L. Length of the plane was L. Then very clearly, if I want to find the time it takes to traverse the length of the plane, starting from rest here, if it started from rest here, and if I want to find the time it takes to traverse the length L, then I can say L must be half of A parallel into T squared, which is like half of G into sine theta minus mu k cos theta into T squared. And I can find the time it takes to traverse to the bottom from the top of the plane if the length of the plane is L. Yes or no? Now another important thing that you might want to know is that, all right, if theta is such that tan theta is more than mu s, we say if theta is more than tan inverse mu s, if theta is more than tan inverse mu s, it's going to slide down the plane. But if theta is less than tan inverse mu s, if theta is less than tan inverse mu s, then it will not slide down the plane. For example, suppose I have a situation of this kind. Suppose this is an inclined plane and body of mass m, and let's say mu s is 1 by root 3 for this situation. Mu s is the coefficient of friction between m and the inclined plane, and this is a fixed inclined plane. Now, what should theta be so that it slides down the plane? Theta should be such that tan theta must be, for it to slide down the plane, to successfully slide down the plane, tan theta must be greater than mu s, greater than or equal to mu s. That means tan theta must be greater than or equal to 1 by root 3, or theta must be greater than or equal to 30 degrees, because this is tan 30 degrees, right? This is tan 30 degrees. That means theta must be greater than or equal to 30 degrees for it to slide down the plane. Yes or no, right? So then, if this angle is 45 degrees, for example, it will slide down the plane. For this situation, if mu s is 1 by root 3, if mu s is 1 by root 3, and this theta is more than 30 degrees, it will slide down the plane, right? It will slide down the plane. But if theta is less than 30 degrees, then friction can hold it back for the same value of mu s. That is to say, and these are important things. You must take cognizance of these things. Must remember these things. Suppose for the same situation where mu s is 1 by root 3, all right, as I start with a value of theta equal to 10 degrees. Will it slide down the plane? No, it will not slide down the plane. If I increase theta equal to 10 degrees and then I say I make it 15 degrees, will it slide down the plane? It will not slide down the plane because theta is less than 30 degrees. It will not slide down the plane. 25 degrees, will this mass slide down the plane? No. But 30 degrees? When theta becomes 30 degrees, it will be on the verge of sliding down the plane. It will be on the verge of sliding down the plane. When theta becomes 30 degrees, it will be on the verge of sliding down the plane, and friction between the mass m and the inclined plane would have reached its maximum possible value, F max stat, right? And under such a situation, mg sine theta would have been F max stat. But, so this is for theta equal to 30 degrees. But suppose theta is some other value, say theta is 20 degrees suppose. Then will it slide down the plane? It will not slide down the plane. then this will be mg sine theta. Mg sine theta. It will not slide down the plane because mg sine theta is not good enough to overcome friction, and the value of friction then will not be maximum static. The value of friction F would be such that it will only balance mg sine theta. It will balance only mg sine theta. Yes or no? Right? Now, suppose theta is more than 30 degrees. Suppose theta is more than 30 degrees. Take this for example. Say theta, for the same situation, mu s is 1 by root 3 gives me theta equal to 30 degrees as the borderline value of theta for which sliding commences, right? Suppose theta is 45 degrees. Suppose theta is 45 degrees. Will it slide down the plane? Yes, because tan theta is more than mu s. Tan 45 degrees is more than 1 by root 3. So yes, it will slide down the plane. It will slide down the plane. There will be mg sine theta acting like this, right? Normal reaction N would just balance mg cos theta. Mg cos theta would be balanced by normal reaction in this case. And frictional force would be mu times n, mu s times n. Assuming static friction, kinetic friction are roughly the same, it's going to be mu s times n. Or if you want to take kinetic friction, then you can say it's F, it'll become kinetic friction, which is mu k times n. And the net force is going to be mg sine theta minus mu k n, where n is mg cos theta. It'll slide down the plane with an acceleration. So what you must remember in fixed inclined planes is that if a particle is put in an inclined plane which has coefficient of static friction mu s, then the limiting value of theta for which it will not slide down the plane is given by tan theta equal to mu s. Values of theta less than this theta will prevent it from sliding down the plane. For theta more than this theta given by tan theta equal to mu s, it will slide down the plane, and the frictional force is going to become kinetic friction. Yes or no? So these are some very basic but very important fundamentals that you must take cognizance of and must remember these results. Thank you so much. We'll catch you in a little while. Bye. Situation on friction. So here we have two blocks, 10 kg block and 20 kg block, resting on a surface, horizontal surface, right? And the maximum static friction between the 10 kg block and the ground is 90 newtons, maximum static friction. And the maximum static friction between the 20 kg block and the ground is given to be 60 newtons. There is a force of 120 newtons acting this way, and there is a force of 100 newton force acting that way. What we want to be able to find is the tension in the string. We want to be able to find the tension in the string. That's what we want to be able to do. Now, the issue here is very pertinent. Whether the system will actually move. See, if there was no friction, if this entire thing was smooth, then this 120 newtons, more than 100 newtons, and the whole thing will drift leftwards. That's fine. But now there is friction. The question is, this 90 Newton force here, which is maximum static on this, and maximum static on this 60 Newton, whether it's going to at all move or not move. Whether friction will prevent it from moving, friction along with tension and these two forces, whether they will keep it in equilibrium or will it accelerate to the left, right? We do not know. We do not really know. What we assume is, let's assume to begin with that it does move to the left. Let's assume that it does move to the left. Now, if it does move to the left, if this does move to the left, then the force of friction between these two would have reached maximum static friction, and this would have been a frictional force of 90 newtons to the left, to the right. Tension would have been then, to balance 120 newtons, tension would have been 30 newtons. Now, let me see if this 30 Newton tension is consistent with the other block or not. Because if this is moving leftwards with a certain acceleration, this must also move leftwards with the same acceleration because of a string constraint. Now, look at this block. So this must also move, and then the tension force here is 30 newtons, right? Is 30 newtons. Now, realize that for this to move to the left, one thing, if it's moving in this direction, frictional force is acting on it in this direction. How much of frictional force is acting on it in this direction? 60 newtons, because it's moving leftwards and there is maximum static already reached between these two blocks. Yes or no? But then there is a problem here. There is a problem. What's the problem? The problem is that this 30 newtons is less than 160 newtons, so it cannot move. It cannot move. It's not possible for this system to move to the left. So one thing for sure, the system didn't move leftwards. It remained static. Now, if it did remain static, let's redraw and re-evaluate the situation. So there is this 10 kg block, there is this 20 kg block, and there is a 120 Newton force this way, and there is a 100 Newton force this way. I know it didn't move. There is tension in the string acting on this in this direction and on this in this direction. Now, if it didn't move, then let me assume that there was static friction reached in one of the blocks. In fact, surely tension would build up only after friction has done its bit. So suppose on the 10 kg block, look at this 10 kg block, which is the front runner, right? On this 10 kg block, let me assume that it's on the verge of sliding. If it's on the verge of sliding, then frictional force on it would be like a 90 newtons this way. And this T then would, in order to balance 120 newtons, would be 30 newtons this way. Now, if this is, so now this is also in equilibrium. So this T is 30 newtons, right? Now 100 Newton is acting to the right. So how much of frictional force must act on it in this direction to keep it in equilibrium? Obviously 70 newtons of frictional force must act on it. But what is the maximum value of static friction that can act on it? 60 newtons. So I cannot have 70 Newton force acting on it. So this cannot be a situation where static friction is reached on this and static friction is not reached on this. I cannot have a situation of this kind. This is just not possible, right? Because it leads, for equilibrium then, I would have required 70 Newton static friction between these two, but the maximum static friction between these two is 60 Newtons. Now, suppose static friction was reached here in the other block. Let me look at the other block. All right, let me draw it right here. That will save me some trouble of redrawing the whole thing. Okay, suppose static friction was reached here, right? If static friction was reached here, realize that this has a tendency to be pulled to the left, right? Tension is acting on it in this direction. Acting on this direction. And suppose there was static friction 60 newtons that has reached between this block and the ground, right? And then very clearly, how much T should be in order, or I'm so sorry. Look at this block independently. Look at this block independently. If you look at this block independently, there is T acting to the left and there is 100 newtons to the right. That means this 100 newtons is trying to pull it in this direction, If it is trying to pull it in this direction, then, and suppose static friction is reached, then there is going to be 60 newtons like this. And if this is going to be 60 newtons, then T would have to be 40 newtons to balance this 100 newtons. T would have to be 40 newtons to balance this. But come down to this. So if T is 40 newtons here, this is 120 newtons, then how much of static friction would be required here? 80 newtons of static friction would be required here, which is all right. So this second situation, let me repeat. One thing that fails is static friction reaching between these two blocks and not reaching between, static friction reaching between this and this and not reaching between this and this has failed, which was this situation. But suppose static friction had reached between these two. Now there is 100 Newton to the right, so static friction will act to the left and would be of value 60 newtons. So then tension has to be 40 newtons to keep this in equilibrium. Now look at this block. There is tension equal to 40 newtons, 120 newtons like this. Now to keep it in equilibrium, friction will intervene. It will provide 80 newtons to the right. But can it provide 80 newtons to the right? Yes, because it's capable of providing all the way to 90 newtons. So this is all right. So tension in the string has to be 40 newtons. Tension in the string has to be 40 newtons. I would think it's an interesting problem. A lot of analysis goes into solving this problem, and a lot of concept is applied in the process. But very soon we'll look at more problems. Thank you so much. Bye. Problem. We have a block of mass m resting on a surface, horizontal surface, where coefficient of static friction is mu s, right? And there is a light inextensible string connecting the block to a fixed wall, right? Now this F is gradually increased from 0 to higher and higher values. This applied force F is increased from 0 to higher and higher values. We want to be able to draw the variation of T versus F. How T varies with F is what we want to plot here. That's what we want to plot here. Now, first things first, what's the maximum static friction? Do you realize that mg acts downwards, n acts upwards? So n obviously is mg. So maximum static friction between the block and the ground is, maximum static friction is like a mu s into n, which is like mu s mg. Mu s mg. Now, what you must understand very clearly and without a doubt is the following. When I apply a small value of F, what triggers first? Tension or friction? Tension or friction? I tell you, friction will trigger first. First, friction will get triggered. It will try to handle F all by itself. Frictional force which will act in this direction, frictional force which will act in this direction will try to handle F all by itself, and tension will be 0, right? It will not create tension initially, right? But as I go on increasing F, capital F, small f will also increase. But then small f, poor fellow, has a limit. It can't go beyond this value, mu s into mg, right? So when F becomes mu s into mg, small f also becomes mu s into mg. But that is its limit. But until then, there is no tension developed. That means when capital F is increased, so I'm talking about tension versus capital F, tension in the string versus capital F. When F is 0, obviously tension is 0. When F is slightly increased, friction becomes equal to capital F, and it prevents tension in the string to develop. That means tension remains 0. Tension remains 0 up to what point? Tension remains 0 up to a value of F, which is like mu s into mg. When F becomes mu s into mg, maximum static friction, then that's the last value of capital F for which no tension would be triggered in the string. That means when capital F becomes like a mu s into mg, until this point, the frictional force would have balanced the externally applied force. But from this point onwards, so after this, F remains constant. Till this point, small f has just kept pace with capital F. Small f has remained equal to capital F till capital F became mu s into mg. But from this point onwards, small f gives in. It remains mu s into mg. Mu s into mg. From this point onwards, what really happens is that any additional value of f, so when f becomes larger than mu s into mg, then what does tension balance? Tension balances capital F minus small f. So when capital F becomes larger than mu s into mg, say greater than or equal to mu s into mg, tension will take care of the difference. Tension will take care of capital F minus small f. capital F minus small f. But f larger than or equal to this, small f will remain mu s into mg. So tension will become capital F minus capital F minus small f. Small f remains mu s into mg. Mu s into mg. But this is only for f from this point onwards, when capital F becomes mu s into mg. So very clearly t versus f is going to be a straight line, because this is a constant, mu s into mg. T versus f is going to be a straight line with slope 1, right? Y equal to mx. So m is 1 here. So it's going to be a straight line with slope 45 degrees from this point onwards. Very clearly, when capital F is mu s into mg, t is 0, and after that t versus f is going to be a straight line as presented here. Yes or no? So I hope you're feeling comfortable with all of this. Thank you so much. More in a little while. Bye. Here on friction, will get you past a lot of relevant stuff. You would know exactly what to do in situations of this kind. What we have is, so it's a very regular standard problem, but you know, if you are able to successfully write your equations, if you are able to successfully draw your free body diagrams, then you know you are in place, you are on job. Look at this problem. There is a block of mass capital M and resting on the ground, and there is friction between capital M and the ground, and that's given to be mu2. Coefficient of static friction is given to be mu2. And then we have a system of pulleys. This pulley integral with the block, and these two fixed pulleys fixed with the wall, right? And then there is a string which goes this way, comes like this, and is attached to a mass small m, which is resting against this vertical wall, right? Obviously small m will descend. Small m descends, you would expect capital M to move to the right. In this situation, we want to find the acceleration of capital M, given that the coefficient of static friction between small m and capital M is mu1, right? So let me assume T is the tension in the string. Few very basic observations here. One, if this block moves to the right by an amount A, if this block moves to the right by an amount A, this length shortens by an amount A, this length also shortens by an amount A. This length remains preserved. That means this length must increase by an amount 2a. That means this mass m will descend by an amount 2a. Yes or no? That means if capital M has a rightward acceleration a, then small m will certainly have a vertical acceleration component 2a. Also, in order that they can preserve contact, in order that they can maintain contact, if this is their common normal direction, by the way, between capital M and small m, this is their common normal direction. If capital M has an acceleration a along the common normal direction, then small m should also have an acceleration a along the common normal direction. That's a wedge constraint. So, and as far as small m is concerned, small m has a vertical component of acceleration 2a, has a horizontal component of acceleration a, keeping commensurate with the wedge constraint, because capital M also has an acceleration small a in this direction, and along the common normal direction, to maintain contact, they must have the same acceleration. All right. T, we have assumed, is the tension everywhere. So let's draw the free body diagrams of small m and capital M. Let's draw the free body diagrams of small m and capital M. Now for small m, look at the forces acting on small m. There is obviously gravity acting downwards, as you can see here, mg. There is tension T acting upwards, right, which you can see here. There is tension T acting upwards. Now if this moves down, another thing is, there is normal reaction that capital M exerts on small m in this direction, perpendicular to the surface, right? And there is, if this slides down, there is kinetic friction between small m and capital M, we'll assume, is approximately maximum static. So that's going to be mu1n. Mu1n acting upwards, because this is moving downwards, right? Now what are the equations of motion? All right, in the horizontal sense, capital N must be small m into a. So I know capital N in terms of small a. In the vertical direction, it has an acceleration 2a. So mg minus t minus mu1n mg minus t minus mu1 n is small m into 2a. That's the second equation, right? Now, if I combine 1 and 2, I could have eliminated n and I could have written, so I can write capital N as m into a, and I can write the expression for t in terms of small a, right? Now, so that's the story of small m. Let's look at the story of capital M. Let's look at the story of capital M. This is the free body diagram of capital M. Realize what are the forces acting on capital M? Okay, so the pulley attached to capital M, there is going to be T like this, there is going to be T like this, right? If capital M exerts on small m n like this, small m will exert on capital M a normal reaction n like this. Yes or no? If capital M exerts on small m a mu1 n this way, frictional force mu1 n upwards, then small m will exert on capital M a mu1 n downwards. Yes or no? There is weight capital Mg acting, there is normal reaction n prime from the ground acting this way, right? Now, of course there is tension T also here, as you can see. And since this is actually sliding on the ground, we have frictional force mu2 n prime, which is approximately maximum static and also kinetic friction acting to the left, right? Now, let me write the equation of motion of the block capital M in the vertical direction. In the vertical direction, what all transpires? T plus mu1 n, T plus mu1 n plus capital Mg must balance n prime, the normal reaction from the ground. That's this equation. So I can write n prime in terms of A and T. So n prime is written as T plus mu1 n, n we saw was m into A plus capital Mg, right? Now, equation of motion in the horizontal direction. In the horizontal direction, it has an acceleration A, right? And what are the forces that cause it to have an acceleration A? There is T plus T2T minus mu2 n prime, minus n, right? T plus T minus n minus mu2 n prime, right? That's the net rightward force, and that must be capital M into A. That's the fifth equation. We have all in place, and if I eliminate T, n and n prime, eventually we'll get a value of acceleration. If I solve all these equations, this would be our acceleration, 2m minus mu2 into capital M plus small m into g by capital M plus small m into 5 plus twice mu1 minus mu2. Yes or no? So this problem, not difficult, but surely has several elements, and if you want to cement them all together, then this is how they will look, right? You would learn how to draw your free body diagrams in situations that involve friction. You'll know how to deal with the constraint, and you would know how to write your equations appropriately, right? So much so for this problem. We'll see you in a while. Bye. This one problem on friction involves 3 blocks A, B, and C. And the coefficient of friction between any pair A and B, B and C and the ground is given to be 0.25, That's given. And A is, attached to the wall by means of a light fixed rod. This is a rod, right? Keeping it fixed to the wall. Now, their masses are given 3 kg, 4 kg, and 8 kgs. What I want to find here is the value of F so that C moves in this direction with a constant velocity, right? Now, very clearly, if C has to move in this direction, right? C has to move in this direction with a velocity v. That means, this has to move in this direction with a velocity v, right? Now, that means the net of all forces acting on B and C must be 0. How do you deal with it? First of all, let me look at A and B, the pair A and B, and find out the force of friction that A will exert on B. One thing for sure, A is fixed, B is moving in this direction, so A will exert on B a frictional force F1 like this. A will exert on B a frictional force F1 like this. And this will be kinetic friction, which is approximately maximum static friction. So mu is 0.25. I'm assuming it's both equal to mu k and mu s. So F1 as the force of friction between A and B. Look, this is A, 3 kg, and B will exert on A or normal force N1 like this. There is Mother Earth, 30 newtons acting this way. So very clearly N1 is 30 newtons. N1 is 30 newtons, right? And F1 therefore would be mu times N1. So F1 would be mu times N1. F1 is mu times N1. Mu times N1, where N1 is 30 newtons, right? So that's the force that A will exert on B, because B is sliding this way, A is fixed. So A will exert on B a force of friction F1 like this. B in turn will exert on A force of friction F like this, but A is incapable of moving in this direction because of the rod, right? Now, force of friction between B and C. Force of friction between B and C. So first of all, I need to find the normal reaction between B and C. So what I do is, I look at a free body diagram that comprises of A and B. Free body diagram that comprises of A and B. A is like 3 kgs, B is like 4 kgs. So obviously, Mother Earth, 7 kgs, so 70 newtons like this. So the normal reaction that C will exert on B is going to be N2 equal to 70 newtons. 70 newtons. N2 would be 70 newtons. Now, if N2 is 70 newtons, realize that C is sliding this way, B is sliding this way, right? So the relative motion of B with respect to C is like this. So C will exert on B a force of friction F2 like this. F2 like this. And F2 would be mu times N2. So what is F2? F2 is mu times N2. F2 is mu times N2, where N2 is 70 newtons. So I know F2. So the force of friction that C exerts on B is F2 like this. F2 like this, right? Now, let me look at, so on B, what are the forces acting? There is F1, force of friction that A will exert on B, which would be like this. And F2 this way, which is the force of friction that C exerts on B, which is like this. And there is tension T like this. And there is tension T like this. So would you not want to believe, if I just look at the free body diagram of B alone, what are the forces horizontally acting on it? Force of friction F1, that's A will exert on B, and a force of friction F2 that C will exert on B, and there is tension T, right? Now, can I calculate tension T? Yes, because B is moving with constant velocity, acceleration of B is 0, so T must just balance F1 plus F2. So I know the tension in the string, which is F1 plus F2. F1 plus F2 means what? Which is like mu times N1 plus N2, which is mu, which is 0.25 into N1 plus N2, that means 30 plus 70 plus 70, 100. So that makes it 25 newtons. 25 newtons is the tension in the string. Mu times N1 plus N2. N1 is 30, N2 is 70 newtons, right? So I know the tension in the string. Now, if I look at the free body diagram of C alone, look, first of all, let me find out the normal reaction N3 that the ground will exert on C. Let me look at the free body diagram of A, B and C. There is 3, 4, 7 and 8, 15. 150 newtons Mother Earth. If I look at A plus B plus C, so N3 must just about balance 150 newtons. So I know N3, which is 150 newtons. And since C is moving to the left on the ground will exert on C a force of friction F3 like this, which is going to be mu times N3. That means 0.25 into 150 newtons, right? Which is like 1/4, so 37.5 newtons is F3. Now let me look at the free body diagram of C alone. So if I looked at C alone, there is capital F in this direction. There is tension T like this. There is tension T like this. And there is F3 like this. F3, which we have computed, is 37.5 newtons. T, which we have computed, is 25 newtons, and realize that if C exerts on B F2 like this, B will exert on C and F2 like this. F2 is what? F2 is mu times N2. That means 0.25 into 70. 0.25 into 70 is F2. F2 is 0.25 into 70. Therefore, now again, this fellow is moving with constant velocity, means zero acceleration. That means net of all forces must be zero. So F then must do what all? Must balance F2, which is 0.25 into 70, must balance T, which is 25 newtons, and must balance F3, which is 37.5 newtons. How much does it turn out to be? This is 1/4 of 60. 17.5 plus 25 plus 37.5 newtons, right? Which is 54, 55, 55 and 25, roughly 80 newtons. I hope I have not made a goof up in my computations. I could have, but you fix it. This is the whole idea then. 17.5, so this is 54, 55, 55 and 25, that makes it 80 newtons. So F, if you apply a dragging force to the left of 80 newtons, then C will move with constant velocity, and because of the string constraint, B will move in this direction with the same velocity. A, because again of the rod, will remain fixed. And this is how you deal with this situation. Thank you so much. Catch you in a while. I'm not going to stop in friction till it all gets really smooth. All right. So the journey starts obviously with basic simple things. Once we get a hang of very basic fundamentals, the essentials, the quintessentials, then we are on with the job. Every other thing then will only be a combination of those very basic, simple, elementary stuff. Now, this time, we have this situation where there is a block of mass 1 kg, and there is a plank of mass 2 kgs. And this surface is smooth, but there is friction between M1 and M2. And the coefficient of friction is given to be 0.5. If nothing is given, you can assume coefficient of static friction to be equal to coefficient of kinetic friction, and so on and so forth. There is no loss of generality if I assume that in absence of further information or data. So now, what is given? So this interface is rough. It has coefficient of friction 0.5. You can assume mu s and mu k both to be 0.5. And this one is imparted a rightward velocity of 10 meters per second. We want to find the time. We want to be able to find the time in which M1 comes to rest with respect to M2. That means the relative motion between M1 and M2 ceases. First of all, understand that if there is friction between M1 and M2, what is it going to oppose? It's going to oppose relative motion. And if it is going to oppose relative motion, then it would try to make sure that the relative motion becomes zero. That means it would try to ensure that the velocity of M1 after a certain time is the same as velocity of M2, right? Now, we want to find that time in which relative motion ceases, the velocity of M1 becomes equal to velocity of M2. But let's physically try and analyze the situation first. So look at M1. Look at M1. Free body diagram of M1. What are the forces acting on M1? There is obviously M1G acting downwards. And there is normal reaction between M1 and M2. M2 will exert on M1 a normal reaction N like this. And in absence of vertical acceleration, N in this case balances M1G, right? And there is friction between M1 and M2, kinetic friction, because there is relative motion at time t equal to 0, there is relative motion. So there is kinetic friction between M1 and M2, and that's going to be Fk equal to mu times N, which is mu times M1G, which is mu times M1G. That's kinetic friction between M1 and M2. Now the direction in which it acts. On each of them, it will act in a manner that will oppose the relative motion of one with respect to the other. So Fk, that's the frictional force existing between M1 and M2, and we are certain about this because there is actual relative motion. So the value of friction would be kinetic, and that would be unique. If there was no relative motion between two surfaces, then frictional force would lie anywhere from 0 to maximum static. But if there is actual relative motion between two surfaces, we know at least for sure that the magnitude of frictional force is going to be kinetic, which is mu times n. So mu, which is given to be 0.5 times n, which we have computed as m1g from the free body diagram of m1. Now realize that at this instant of time, this is at rest, and m1 has a rightward velocity. So that means m1, the motion of m1 with respect to m2 is rightward, and that must be opposed by friction. So m2 will exert on m1 a frictional force that will oppose the relative motion of m1 with respect to m2. m1 is trying to move to the right with respect to m2. So frictional force on m1 that m2 exerts would be to the left, Fk. Fk would be to the left. Yes or no? That will be the direction of the frictional force that m2 will exert on m1 to oppose relative motion, because m1 has a m1 is moving to the right with respect to m2, which means now the velocity of m1 is v0 to the right, whereas frictional force is acting on it to the left. That means it's now going to retard. That means velocity of m1 will decrease. Yes or no? Velocity of m1 will decrease. So if the initial velocity is 10 meters per second, subsequently the velocity will decrease, right? And what would be the retardation produced on m1? The retardation produced on m1 would be of magnitude a. See, this is the only horizontal force acting. So the leftward acceleration would be Fk by m. The leftward acceleration of this would be Fk by m. Because Fk is the leftward force, this is the leftward acceleration, which is Fk by m, which is mu g. So this has a retardation mu g, because its velocity is to the right, acceleration is to the left. So there is retardation produced on this, and of magnitude mu g. Now let's go to m2. What about m2? Now for m2, realize the free body diagram. Of course, there is m2g downwards, and there is normal reaction from the ground, n1 upwards. And if m2 exerts on m1 a leftward frictional force Fk, m1 will exert on m2 a rightward frictional force Fk. Yes or no? This is m2, right? And it's initially at rest and has a rightward force acting on it, so it will accelerate. Its acceleration is going to be a prime, which is going to be okay, so the frictional force Fk divided by m2. Fk is like a mu m1g divided by m2. That's going to be the acceleration of this to the right. So this will gain velocity to the right. The velocity of this to the right will decrease. Yes or no? Now, t seconds later, the velocity of m1 will become what? T seconds later, the velocity of m1 will become v equal to v0 minus acceleration, which is mu g, into t, right? That's going to be the velocity of m1 t seconds later. Velocity of m2 t seconds later is going to be, say, v prime. V prime is going to be a prime into t. A prime is this. Because initial velocity is 0, v equal to u plus at is what I am applying, is going to be mu times m1 by m2 into g into t. At. That's the velocity of m2 t seconds later. That's the velocity of m2 in the rightward direction t seconds later. Now, very clearly, v is decreasing with time, whereas v prime is increasing with time. The velocity of this is very clearly v, which is decreasing with time, and the velocity of the lower mass is increasing with time. You would expect at some instant of time v to become equal to v prime, and when v becomes equal to v prime, v prime, relative motion ceases. So we want to find that instant of time when v becomes equal to v prime. So v is v prime, or v0 minus mu gt, t equals v prime, which is mu times m1 by m2 into g into t. Yes or no? Right? So all that we need to do is we need to solve for t. So then t turns out to be V naught divided by mu g into 1 plus m1 by m2. m1 by m2. That's the instant of time. See, if I solve for t, I transpose this on this side, take mu gt common, and then what I'm left with inside the parenthesis is 1 plus m1 by m2. That's v naught. So v naught by this, and what does this turn out to be? This is 10. V naught is 10. Mu is 0.5. Mu is 0.5. 0.5 into 10 is 5 into 1 plus m1 by m2. m1 by m2 is half. This is what happens. So this is like 4 by 3. Do you realize this becomes 2, 2 to the 4, 4 by 3. So after t equal to 4 by 3 seconds, the velocities of the two masses will become equal, relative motion will cease, frictional force will now cease to exist. Beyond this point, frictional force will cease to exist. Frictional force will become 0. Once both masses move with the same velocity to the right, which will happen t seconds later, then we are all done. Yes or no? Right? So, again, a problem that delivers is simple but delivers a lot of relevant instruction, information, and analysis. Must keep this in mind. Whatever I have done here could be really a constituent of several more complicated, involved, interesting, bizarre problems. Thank you so much. Promise to get back in a little while. Bye. Tenets of friction. Once again, with a simple but relevant situation. Here we have a plank of mass m resting on a smooth horizontal surface. And there is a man of mass small m that is moving on the plank with an acceleration a with respect to the plank to the right. A is not the absolute acceleration of man, is not the acceleration with respect to the ground. A is the acceleration of the man with respect to the plank in this direction, in the leftward direction, Now, what are the things that we want to find? We want to find the acceleration of the man and the plank in the ground frame of reference, 1. 2, we want to be able to figure out the frictional force between the man and the plank. After all, if the man is moving with respect to the plank in this direction, it's because frictional force is aiding the man to move in this direction. That means the plank must be exerting on the man a frictional force leftwards, this way, right? So let me draw the free body diagram of the man. There is mg like this. Then the plank will exert on the man a normal reaction n like this. And to aid the acceleration of man in this direction, the plank will exert on the man a frictional force F as shown. So that's a free body diagram of the man. Now, free body diagram of the plank. This is the plank. This surface is given to be smooth, right? There is, if the plank exerts on the man a normal reaction n like this, the man will exert on the plank a normal reaction n like this. If the plank exerts on the man a frictional force F like this, as you can see, the man will exert on the plank. If the plank exerts a force F like this, the man will exert an equal and opposite force F like this, courtesy Newton's third law. Also, there is weight of the man, mg, acting downwards, and there is normal reaction n prime from the ground, right? This is the sum total of things acting on the plank and sum total of things happening on the man, plank and the man. Now, because of this force, the plank has an acceleration a1 to the right, right? So if I have to write equation of motion of the plank in this direction, can I not say F is ma1? Could that be said? The plank side of the story, ma1, where a1 is the acceleration of the plank in the ground frame. Right? Now, the acceleration of the man with respect to the plank is a, right? That is the relative acceleration of the man with respect to the plank. Now, if I add to it the acceleration of the plank, I'll get the acceleration of the man in the ground frame. What would be the acceleration of the man in the ground frame? The relative acceleration a with respect to the plank plus the acceleration of the plank, right? The acceleration of the man in the ground frame is going to be what? Acceleration of the man in the ground frame is going to be acceleration of the man with respect to the plank, that is the relative acceleration, plus the acceleration of the plank, right? So the magnitude of acceleration of the man in the ground frame, A, is going to be what? In the ground frame, the acceleration of the man in the ground frame, let me call it AM. The magnitude of this is going to be acceleration of the man with respect to the plank, which is leftwards, which is given to be A, plus acceleration of the plank, which is in this direction. So minus A, right? Acceleration minus A1, right? So A minus A1 is the absolute acceleration of the man with respect to the ground. Why? Because A is the acceleration of the man in the ground with respect to the plank, and minus A1 is the acceleration of the plank, right? I've taken leftward positive, rightward negative. So A is the relative acceleration of the man with respect to the plank, plus minus A1. Minus A1 is what? Acceleration of the plank in the ground frame. Acceleration of man with respect to the plank plus acceleration of the plank will give you acceleration of the man in the ground frame, which is A minus A1. So A minus A1 is the acceleration of the man in the ground frame. And what causes this acceleration in the ground frame? F, right? See, after all, if I have to apply Newton's second law to the man, I must know the acceleration of the man in the ground frame, because I know the force F acting on the man, and this force F will cause an acceleration in the ground frame, which is A minus A1. So this F is applied to the man is going to be M into A minus A1. Yes or no? Now, very clearly, I can solve for A1 from this equation. A1 turns out to be what? So A1 is A minus A1, which is the acceleration of the plank. A1 turns out to be A by 2. A1 turns out to be A by 2, the acceleration of the plank. And what is F? F, the frictional force between the two, is going to turn out to be MA1, which is MA by 2, right? And what is the acceleration of the man in the ground frame? A minus A1. A minus A by 2, that makes it A by 2. Yes or no, right? So, yet another problem which actually saw us through a set of very important, relevant, pertinent concepts on friction, but we are not done yet. Very shortly, I'll join you with more stuff. Thanks so much. Bye. Another situation, not a difficult one, but again, like I said, I'm trying to do pertinent things that will lead you into conceptual understanding of friction. So this time we have a plank of mass capital M resting on a ground, and there is frictional force between the plank and the ground, and coefficient of friction is given to be mu. There is a man, and the man has an acceleration A in the ground frame on the plank without slipping on the plank. We want to be able to find the values of A, or the range of A, for which the plank does not slip on the ground. This is what we need to do. Simple. Look at the man side of the story. What are the forces acting on the man? Mg, and normal reaction N equal to N must balance Mg, right? And in order that he could have had an acceleration A to the right, the plank must exert on the man a rightward force, frictional force, enabling a rightward acceleration A. So very clearly, F1 we know must be mass into acceleration from the man side of the story. F1 must be mass into acceleration A. That's one, right? Now, look at the plank. So another thing, for the plank, if you look at the plank plus the man together, then the normal reaction between the man and the plank is internal, and then the normal reaction from the ground, N prime, that the ground exerts on the plank must just balance capital M plus small m into G, or N prime could have also been obtained by looking at the free body diagram of the plank. If you look at the free body diagram of the plank, there is capital Mg downwards, and if the plank exerts on the man a normal reaction N upwards, the man must exert on the plank a normal reaction N downwards. Yes or no? And N prime must balance N plus Mg, which is like N is N plus capital Mg, which is like small m plus capital M into G. Or I could have obtained N prime straight out of the free body diagram of the two together. N prime could have been obtained as capital M plus small m into G by looking at their free body diagrams together. So I also know the maximum static friction between capital M and the ground, right? So what's the value of the maximum static friction between capital M and the ground? Static friction between capital M and ground, what's that supposed to be? That's going to be mu times n prime. That is mu times capital M plus small m into g, right? Now, if the plank exerts on the man a frictional force F1 to the right, the man will exert on the plank a frictional force F1 to the left, right? Now, based on the value of F1, which will depend on the value of A, right? The value of F1, like you see here, will depend on the value of A, right? So, based on F1 and capital F, the plank could have a tendency to move to the right, or it could have a tendency to move to the left, right? Suppose the plank, there is a certain value of A which causes the plank, there is capital F acting on the plank like this, there is F1 whose value is m into A acting on this, right? Suppose the plank has a tendency to move to the right. Suppose the plank has a tendency to move to the right. If the plank has a tendency to move to the right, frictional force that the ground will exert on the man will be F2 to the left. Will be F2 to the left. Yes or no? And since I don't want the plank to move, capital F must just balance F1 plus F2. Balance F1 plus F2 because the plank has a tendency to move to the right. The ground exerts a frictional force F2 on the plank to the left. F2 then turns out to be capital F minus F1. F1 is MA. But we know that F2, the frictional force between the ground and the man, cannot exceed this value. So cannot exceed mu times m plus small m into g, right? So this gives me like a MA greater than or equal to F minus mu into capital M plus small m into g. So that gives me A must be larger than or equal to F by M minus mu into capital M plus small m into g by m. So surely A must be larger than this. Now there is a second situation possible. What's the second situation? The second situation is, look at the plank. Capital F to the right. There is frictional force F1 whose value we know is mass into acceleration for the man. And suppose the plank has a tendency to move to the left. Suppose the plank has a tendency to move to the left. Then the frictional force F2 will act on it to the right. And then we have F plus F2 is F1 because we don't want the plank to move. F plus F2 must be F1, or we have F2 equal to F1 minus F. F1 is m into A minus capital F, right? But realize F2, which is also static friction between capital M and the ground, cannot exceed maximum static friction. So this has to be less than or equal to mu times capital M plus small m into g. F2 cannot exceed this value, which leads us to believe that A has to be less than or equal to mu into m plus small m into g. Right from this equation, A less than or equal to dividing by small m plus F by m. Yes or no? Right? Which means there is a range of A. A must be less than this but greater than this value, right? So we essentially then have A less than or equal to this value, which is mu by small m into capital M plus small m into g plus F by m, but has to be larger than or equal to this value, greater than or equal to F by small m minus mu into capital M plus small m into g by small m. That must be the range of A for which the plank doesn't slip on the ground. And you know, again, the problem is not difficult. It's culmination of a large number of simple little facts, simple little stories on friction, but it'll certainly bring you good wisdom. It'll give you greater comfort. It'll give you superior confidence. Thank you so much. More in a little refer to this situation, a special situation on friction, where we have an inclined plane of mass capital M on a smooth horizontal surface. And there is a block of mass small m on the inclined plane as shown. right? And the coefficient of friction is mu between small m and the inclined plane. Between small m and the inclined plane, the coefficient of friction is mu. Now, we want to be able to find the range of F. The objective of this problem is to find the range of F, which will prevent small m, from slipping down the plane, which will prevent small m from slipping down or up the plane. That means we don't want relative motion between small m and capital M. We don't want small m to go up the plane, and we don't want small m to go down the plane, right? So for sure, you know, there could be a value of capital F for which small m has a tendency to move down. Friction will then act on it upwards, right? There is a certain value of capital F or a range of capital F for which small m has a tendency to move up, and if it has a tendency to move up, frictional force will act on it downwards, right? Now, of course, you know, we don't want to guarantee that there is no relative motion between small m and capital M. What must necessarily happen is that the value of small m should not exceed maximum static friction. The value of small f should not exceed maximum static friction between small m and the inclined plane. Now, let's look at the forces involved. On small m, there is mg, and there is normal reaction, and there is mg cos theta and mg sin theta. Mg could have been resolved as mg cos theta and mg sin theta. In addition, either friction could be acting upwards or friction could be acting downwards, depending on the value of capital F, whether small m has a tendency to move down or small m has a tendency to move up. Friction will act this way or this way, right? Now, what is it that we are looking for in terms of capital F? We are looking for no relative motion between small m and capital M. If we are looking for no relative motion between small m and capital M, we are anticipating or expecting small m and capital M to have a common acceleration a to the right. So if I have to apply equations of motion to capital F plus capital M plus small m to the right, with no relative motion between them, that means they have a common acceleration a to the right. And if I apply a force F, then, you know, the frictional force, the normal reaction between small m and capital M, etc., they are all internal forces. Of course, the normal reaction from the ground and mg downwards, they don't participate in the horizontal direction. So capital F must be capital M plus small m into A, right? So A must then be capital F by capital M plus small m. That's the common acceleration rightwards of small m and capital M. This is what we want, right? So if they have a common acceleration to the right, there is no relative acceleration between small m and capital M. Now, look, as far as acceleration is concerned, this is A, which is capital F by capital M plus small m. That's a horizontal direction, and this will make with the slope. This is the slope, right? This is slope. This is parallel to the slope, an angle theta, right? The horizontal direction will make with the slope an angle theta. So if this is theta, this is also theta, right? And A has components like A sin theta perpendicular to the plane for small m and A cos theta parallel to the plane, right? This is what it is. And what provides A sin theta? A sin theta is provided by the difference of n and mg cos theta in either case. So I know n, and then n minus mg cos theta in all circumstances must provide for A sin theta for small m. Must be small m into A sin theta, right? So that gives me capital N, the normal reaction between the two, as mg cos theta plus ma sin theta. Good. So I know the normal reaction between small m and capital M. Now, suppose the mass capital M has a tendency to move up like the plane, has a tendency to move down, then frictional force will act this way, right? So now if frictional force acts upwards, in this case F, then realize that A cos theta, the acceleration of small m in this direction, is provided for by mg sin theta minus F, right? So I'm now talking of this case. I have like a mg sin theta minus F when this has a tendency to move down, frictional force will act upwards, mg sine theta minus f. So this is as per the free body diagram of small m. Mg sine theta minus f must give this an acceleration a cos theta parallel to the plane, m into a cos theta, right? Now small f, if I solve for small f is like mg sine theta minus ma cos theta, and very clearly this small f, if there is no relative motion between small m and capital M, the frictional force cannot exceed maximum static friction. So this small f must be less than or equal to maximum static friction, which is mu times n. Mu times n, this n I can replace by mg cos theta plus ma sin theta. So this is like mu times n, n is mg cos theta plus ma sin theta, right? Now let me look for the range for A. Let me transpose this ma on this side. So if I transpose ma on this side, then I get like a mu sin theta plus cos theta, mu sin theta plus cos theta greater than or equal to mg into sin theta minus mu cos theta. Transpose this on this side and this on this side, mg into sin theta minus mu cos theta. That means I can cancel m from both sides, so I must have a greater than or equal to g into sin theta minus mu cos theta, right? G into sin theta minus mu cos theta divided by mu sin theta plus cos theta, right? And if this be the case, a I can replace by capital F by capital M plus small m. So a, right here, a if I replace by capital F by capital M plus small m, that's a greater than or equal to g into sin theta minus mu cos theta divided by mu sin theta plus cos theta. So that gives me f greater than or equal to m plus m into g into sin theta minus mu cos theta divided by mu sin theta plus cos theta, right? So if f is larger than or equal to this value, f has to be clearly larger than or equal to this value, which means that that's for this situation. That means when this has a tendency to move down, frictional force will act on it upwards. Let me put this result. I hope you've been able to copy this part. And so one situation that we already have with us is f greater than or equal to m plus m g. I'm just copying this so that I can create room on the board, minus mu cos theta divided by mu sin theta plus cos theta, right? That's one. Now if you allow me to remove the clutter from here, so I've handled this situation. Now I'm going to go to this situation if it gives me some additional limits on f, right? So if I remove the clutter from here, only with a view to address this situation, where the values of f are such that this has a tendency to move up and therefore frictional force will act on it downwards. Now look, let me get down to this. This time frictional force is acting downwards. So let me just, in this diagram itself, let me put frictional force F downwards. N, like before, remains the same. N will balance mg cos theta. N minus mg cos theta will provide ma sin theta. So that will not change, right? Now, what about the acceleration a cos theta parallel to the plane? Acceleration a cos theta parallel to the plane is provided for by mg sin theta plus f, right? mg sine theta plus f is instrumental in providing small m and acceleration a cos theta in this direction, right? Both capital M and small m have a common acceleration a to the right, which I have resolved perpendicular to the plane and parallel to the plane. So parallel to the plane, if I have to write equations of motion for this situation in which friction is acting downwards, then I have clearly f plus mg sine theta, f plus mg sine theta taking care of bringing about ma cos theta, right? Or f then turns out to be ma cos theta minus mg sine theta, right? Ma cos theta minus mg sine theta, and that cannot exceed maximum static friction. So that must be less than or equal to mu times n. But what's n? N is this. So I end up getting ma cos theta minus mg sine theta less than or equal to mu times n, which is this. Sine theta, right? And then the range on A, MA I transpose on this side. I get MA into, or I can say cos theta minus mu, I transpose this on this side, cos theta minus mu sine theta less than or equal to mu times, so I take these two mg common, ma cos theta minus mg sine theta, ma cos theta plus ma sine theta plus mg cos theta, right? And ma, so alright, so less than or equal to, I transpose this on this side, so mg I take common, sine theta plus mu cos theta, and m gets cancelled, and this a I replace by capital F by capital M plus small m, and that gives me f less than or equal to capital M plus small m into g into sine theta plus mu cos theta divided by cos theta minus mu sine theta. Right, this is what I get. So f has to be larger than or equal to this value and smaller than or equal to this value. So f has to be in this range. This is the maximum possible value of f that you can apply, and this must be the smallest value of f you must apply so that there is no relative motion. Yes or no? Right? This is the smallest value of f that you must apply, this is the largest value of f that you must apply, and therefore you know the range of f for which there would be no relative motion between capital M and small m, and small m will remain at rest with respect to capital M. Again, an important situation, a relevant situation, and you would encounter similar things, or this will become part of many more problems. So if you understand all the ideas communicated here, then you're doing good. Thank you so much. Bye. Come up with another interesting but simple and common situation. We have a latch B of mass m that lies in a vertical sleeve, and one end is inclined at an angle 45 degrees. This face is inclined at an angle 45 degrees with the horizontal, and it's in contact with a horizontal member A whose interface matches with B at an angle 45 degrees with the horizontal. Now the vertical sides of this unit, they are smooth, but the interface between A and B is rough. And the coefficient of friction at this interface is mu equal to 0.4, is coefficient of static friction. And both A and B are of mass m. What we want to do is, and you know, A is capable of moving into the horizontal channel, So while A transits into the horizontal channel, B gets raised. And while B gets raised, there is relative motion at this interface. There is relative motion between A and B at this interface. But initially, so what I want to do here is, I want to find the minimum value of f for which B starts to move, up. Now, So as I go on increasing f, what really happens is b, for small values of f, b does not get raised. There is friction between a and b. Which is less than maximum static, and there is no relative motion. It's able to prevent relative motion at this interface. But for a certain value of f, friction at the AB interface becomes maximum static. That means if n is the normal reaction between A and B, frictional force at this interface becomes mu n. And that's the value of f for which it's B is on the verge of getting raised, but still in equilibrium. So both A and B would be just about in equilibrium, but A on the verge of sliding horizontally and B on the verge of moving vertically. I want to find that minimum value of f, essentially, for which at this interface friction becomes maximum static. Right? For values of f smaller than that, friction at this would be less than maximum static. Both A and B are given to be of mass m. Now, one very basic thing. If n is the normal reaction between A and B, which acts on B like this, perpendicular to this interface, on A acts like this, perpendicular to this interface, and this n in both cases makes an angle 45 degrees with the vertical, which you can check geometrically. Then, since A has a tendency to move in this direction, frictional force on A will act along the interface and would be of magnitude mu n like this. Frictional force on B would have just about reached its maximum static and would be mu n like this, right? Now, so that's the f that we want, for which this frictional force between A and B just about reaches its maximum possible, and there is relative motion that is on the verge of commencement. B is about to get raised, A is about to move horizontally, but in equilibrium until such an instant. Now if I look at the free body diagram of B, what's the free body diagram of B? Look, there is mu n, which is frictional force on B acting in this direction, frictional force mu n acting on A in this direction. There is normal reaction that A will exert on B perpendicular to this 45-degree interface, so n will make an angle 45 degrees with the vertical. There is mg like this. Now, of course, there are lateral forces from these sides. We are not interested in the lateral forces acting on B. We are interested in the vertical forces. Now, what are the vertical forces? There is mg like this. There is n by root 2 n cos 45 degrees upwards, and then mu n has a vertical component, downward component, which is mu n cos 45 degrees. So what we really have is vertical forces balancing each other, n by root 2 being balanced by mg plus mu n cos 45 degrees, which is this equation, vertical equilibrium of B. Now what about A? This is A. There is mg acting like this, and there are lateral forces from the sides that are holding it. We're not interested in those. There is normal reaction that B will exert on A perpendicular to this, which will make an angle 45 degrees with the horizontal as well as vertical. And there is mu n, the frictional force that B will exert on A, opposite to this mu n, as you can see, right? Now, horizontally, it's an equilibrium, and there is of course an external force F, which is just about maintaining it in equilibrium. Now what happens? What happens is, in the horizontal direction, for A, what are the forces? F taking care of mu n cos 45 degrees. See, this is 45 degrees. So mu n cos 45 degrees, mu n by root 2 plus n cos 45 degrees, which is n by root 2. That's equation 2. That's the equilibrium of this, right? F taking care of mu n by root 2 plus n cos 45 degrees, which is n by root 2. I just need to eliminate n. And solve for F. Realize that from this equation I could have written mg equal to n into 1 by root 2 minus mu by 2, right? Mg equal to n by root 2, mu n cos 45, so this would have been root 2. So I can take root 2 common from this, n by root 2. And this is what? This is n by root 2 into mu plus 1. This equation, all that I need to do is I need to divide this by this so that n gets eliminated. So I then get like a f divided by mg equal to mu plus 1 by 1 minus mu. F then becomes mg into 1 plus mu divided by 1 minus mu. I can plug in the value of mu, m, etc. and get the required answer. So this is the force. If values of F are smaller than this value that are obtained, then the frictional force between A and B would be less than mu n. If F is larger than this, frictional force remains practically mu n, but equilibrium is disturbed. B starts to accelerate upwards, A starts to accelerate rightwards, and so on and so forth. This is the transition point. This is the transition point. I hope all of you understand everything that I have said here. Thank you so much. Bye-bye. Interesting situation with you. We have a platform which is moving with an acceleration A by some mechanism, right? And there are two masses, two blocks resting on this platform, and the coefficient of friction between m1 and the platform and m2 and the platform is given to be mu. And there is a spring in its natural state. There is a spring in its natural length connecting the two masses. Right? The question is, what happens to the spring as A is gradually increased? Starting from smaller values of A to larger values of A, what happens to the spring length? It's in its natural state. As I gradually increase A, what transpires to the spring? That's a question we need to answer here. Now, one thing, what are the forces acting on m1 and m2, any one of the two masses? Let me call the two masses, let's say, as say some m. M could be m1 or m could be m2, right? A common analysis for the two masses. So look at any one of the two masses, m1 or m2, call it m, say for example. Resting on the platform, all right? Now the platform is given an acceleration a to the right. Now m has its weight acting downwards, and there is normal reaction n from the ground, which balances mg. Normal reaction from the ground balances mg. And there is frictional force between m and the platform, right? What would be the direction of frictional force that the platform will exert on m? Obviously to the right, because friction would want small m and the platform to move in sync with each other. That is what would be the objective, right? Now, the question is, what is the maximum possible value of f? F max. Maximum possible value of f would be mu times n, that means mu times mg. That means the maximum frictional force that the platform can exert on m is mu times mg, right? That means, what is the maximum possible acceleration of m? A max, maximum acceleration of small m, is going to be mu mg by m, that means mu g. Mu g is the maximum acceleration. That means if small m relies purely on friction to get an acceleration, if small m purely relies on friction to get its acceleration, then the maximum possible acceleration of small m is mu g, right? That means, if I say for example, if mu g suppose turns out to be say 10 meters per second squared, for example. Say for example, A max, maximum acceleration, turns out to be 10 meters per second squared. Then what happens? Suppose I give it an acceleration of, so one thing for sure, this is not just the maximum acceleration of m, this is also the maximum common acceleration between small m and the platform. Why, you'll see. Suppose I give the platform an acceleration of 5 meters per second squared. Suppose I give the platform an acceleration of 5 meters per second squared. Okay. Now friction, is it capable of giving small m an acceleration of 5 meters per second squared? Yes, because friction can give accelerations to small m all the way to 10 meters per second squared, right? So yes, friction is good enough to give it an acceleration of 5 meters per second squared, right? Suppose I give this platform an acceleration of 6 meters per second squared. Is friction good enough? Is competent enough to give small m an acceleration of 6 meters per second squared? Yes, because friction can support an acceleration of small m up to 10 meters per second squared. Now, so as I gradually increase the acceleration, of the platform, then the frictional force gradually increases so as to support small m getting the same acceleration as that of the platform, right? The moment the acceleration becomes 10 meters per second square, friction reaches its maximum static value mu mg. Friction reaches its maximum static value mu mg, and the mu mg force acting on small m will give small m the maximum acceleration, say 10 meters per second squared, right? But beyond this point, friction cannot increase. That means a maximum force acting on small m can give small m its maximum acceleration of 10 meters per second squared. Frictional force cannot increase beyond this point, mu mg, right? That means the acceleration of small m cannot increase more than 10 meters per second squared, because this 10 meters per second squared is obtained by a maximum value of the frictional force mu mg, right? So which means now if I give the platform an acceleration of 12 meters per second squared, okay, the platform can get an acceleration of 12 meters per second squared, but the value of the frictional force remains mu mg. And if the value of the frictional force remains mu mg, then the acceleration of small m will remain 10 meters per second squared. Suppose I give the platform an acceleration of 15 meters per second squared. Then what happens to the frictional force that the platform can exert on man? It's still mu mg. And mu mg can support only 10 meters per second squared. That means any acceleration over and above 10 meters per second squared, which is the maximum common acceleration of the mass and the platform, will cause the upper mass to have an acceleration of 10 meters per second squared, will cause the upper mass to be acted upon by maximum static friction only, and the lower mass can have its increased acceleration as it wishes, right? But the point is, as I go on increasing A, the frictional force between the platform and m goes on increasing till it reaches its maximum static value. And once it reaches its maximum static value, small m gets its maximum common acceleration. And beyond that point, any further increase in the acceleration of the platform will not cause an increase in the acceleration of small m, because small m is then acted upon by the maximum possible value of the frictional force, and therefore the acceleration of this will remain 10 meters per second squared. That means what? First of all, maximum common acceleration will be mu g, right? That means as long as A is less than or equal to mu g, all the three masses will have an acceleration A, right? The moment A becomes greater than mu g, acceleration of the platform becomes greater than mu g, the upper masses will have an acceleration mu g only. That means the interesting thing is, at all times the upper masses will have the same acceleration. Up to a point it will be less than mu g, then the upper masses receive a maximum acceleration mu g, and then any further increase in A will not cause increase in the acceleration of m1 and m2, that will remain mu g. So the rule of the game here is that m1 and m2 at all times have the same acceleration. If they have the same acceleration, they start from rest, they will at all times have the same velocity, and if they have the same velocity, that means this end of the spring, if it has a velocity v at a certain instant of time, then this end of the spring which is integral with the mass m2 will also have the same velocity v, and if the two ends of the spring have the same velocity, then the spring will not change length. The spring only changes length if the two ends have different velocities, but if at all times the two ends have the same velocity, the spring length will remain constant. That means the spring remains in its natural length irrespective of the value of A. Surely up to A, this as long as A varies from 0 to mu g, as long as A varies from 0 to A max, maximum common acceleration, which is mu g, all three masses are in sync. When A becomes greater than mu g, this will have an acceleration A, but the upper two masses will still have the same acceleration, which was the maximum they could because of friction, which is mu g. Important is that the two masses will have the same acceleration, the ends of the spring will have the same velocity, the spring will remain in its natural length. Thank you so much. Bye-bye. Another situation on friction for you. There is a parabolic bead. This is a bead, say a wire bent in the form of a bead, parabolic bead. This is a wire bent in the form of a parabolic bead. Alright. And the equation of this curve is given as, say, x squared equal to ay. X squared equal to, that means any x and y on this curve is related by x squared equal to ay. What we want to find is the maximum height above the ground, that means the maximum possible value of y. We want to find y max, for which a particle placed on the bead will still be in equilibrium given that the coefficient of friction is mu. Between the particle and the bead, the coefficient of friction is mu. Now, one thing that you must remember is, if there is an inclined plane, say fixed inclined plane, if there is a fixed inclined plane of angle of inclination theta, right? And there is a particle of mass m placed on the inclined plane, and mu is the coefficient of friction between the particle and the sloping surface of the inclined plane. Then, in order that m does not slide down the plane, that means m remains static on the inclined plane, then the condition for that to happen is mu must be greater than or equal to tan theta. It means tan theta less than or equal to mu. If theta is such that tan theta is less than or equal to mu, the particle will remain in equilibrium, right? If there is a fixed inclined plane, you must take notice of this. If mu is greater than or equal to tan theta, or tan theta is such that tan theta is less than or equal to mu, where mu is the coefficient of static friction, then the particle will remain in equilibrium. Now the question is, this is a parabolic bead. How do I connect it with an inclined plane? This is a parabolic bead. Where on earth is the inclined plane? What we can conceive of is, this could be looked upon as an inclined plane whose angle of inclination is different at different points. This whole thing could be looked upon as an inclined plane whose angle of inclination is different at different points. That means at the point P, for example, I can perceive the whole thing at the point P. If I draw a tangent, this is a tangent at the point P. This is a tangent at the point P. And I can imagine the parabolic bead at the point P to behave like an inclined plane of angle of inclination theta. I can imagine the parabolic bead to behave like an inclined plane of angle of inclination theta at the point P, That means, if it is like an inclined plane of angle of inclination theta at the point P, so now this theta is different for different p's, because if I draw tangents at different points, theta would be different for different tangents. So tan theta is the slope of the tangent at the point P, where theta is the angle that the tangent makes with the parabola at the point P. Now, very clearly, how does one obtain tan theta? Tan theta is given by dy dx, where y is x square by a. So this is like d dx of x square by a, which is like 2x by a. At any given x comma y, the bead behaves like, at any point x comma y, the bead behaves like an inclined plane of angle of inclination theta given by tan theta equal to 2x by a. That means, now, in order that the particle remains in equilibrium, we must have tan theta not exceeding mu. Tan theta not exceeding mu. That means 2x by a not exceeding mu for the particle to remain in equilibrium. X can be written as root ay. Very clearly, x can be written as, I could even square this. So 4x squared by a squared is less than or equal to mu squared, right? X square I can write as ay. So if I write x square as ay, because x comma y is a point on the parabola. So this x comma y, right? This is tan theta at any x comma y. That means at this x comma y. This x square I can write as ay. So 4 into y by a. If I write x square as ay less than or equal to mu squared, or y less than or equal to 1/4 mu a squared. Y less than or equal to 1/4 mu a squared. That means the maximum possible value of y, the maximum height above the ground for which the particle can remain in equilibrium is 1/4 mu a squared. Y max is 1/4 mu a squared. Maximum possible value of y is 1/4 mu a squared. Does it make sense to you? Right? So this again I thought was an interesting problem, and one could have looked upon the bead as an inclined plane of variable slope. The slope or the angle of inclination of the inclined plane at any given point is like equivalently the slope of the tangent at that point, and the slope of the tangent at that point, tan theta, is given by dy dx, which is like the equivalent inclined plane at the point P. And the whole idea boils down to mu being greater than or equal to tan theta for the particle to be in equilibrium at P. So mu greater than or equal to tan theta, where tan theta is the slope at x comma y given by twice the x coordinate divided by a, and then I have to find y max. So this x comma y satisfies this equation, so x square can be written as ay. I square this, so 4 by a squared, and this x square written as ay less than or equal to mu squared, or that really gives me x square written as ay. We get y less than or equal to 1/4 mu a squared. That means this then happens to be the maximum possible value of y. So this I thought was an interesting situation. I hope a lot of important and relevant stuff has been communicated to you by means of this problem. Please take proper notice of the sequence of things and the ideas involved in this problem. Going to come in very handy. Thank you so much. Bye-bye. We'll look at a very conceptual situation now. There are two blocks, one of mass 2 kg, one of mass 3 kgs, and they are resting on a horizontal surface. And coefficient of static friction between the 3 kg block and the ground is 0.2, and coefficient of friction between the 2 kg block and the ground is 0.1. There is a 8 Newton force applied to the right. There is a 1 Newton force applied to the left, as shown. We want to be able to find the tension in the string. We want to be able to find the frictional force between the 3 kg block and the ground, the 2 kg block and the ground. These are things that we need to deal with. Now, realize that if the whole thing was smooth, then there would have been a net 7 Newton force to the right, right? That means the whole system now has a tendency to move to the right. And who will counter it or combat it first? The frictional force between the 3 kg block and the ground. So first of all, the frictional force between the 3 kg block and the ground would try to do its bit, the maximum bit it could. If it can handle it enough, then tension won't come into the picture. But if it cannot provide enough, then there is a differential tension that comes into play, and which would try to put the 3 kg block in equilibrium, if at all, right? And then of course there will be tension acting on the 2 kg block to the right. There is frictional force between the 2 kg block and the ground, and 1 Newton. We'll have to see if maximum static friction or less than that can prevent 2 kg block from moving. All right. So first of all, let me compute maximum static friction here. Maximum static friction here is going to be mu s mg. Mu s mg means 0.2 into 3 into 10. These many newtons, that means 6 newtons is maximum static friction between these two. What's the maximum static friction between these two? Is mu s into 2 into 10. That is 2 newtons is the maximum static friction between these two. All right. So let's start focusing on the 3 kg block first, because the first friction that is going to come into picture is going to be this, because the whole thing has a tendency to slip to the right, and therefore friction would try to prevent the 3 kg block from sliding on the ground, because the 3 kg block has a tendency to slide to the right because of the 8 Newton force. So now what's the maximum value of the force? Frictional force 6 newtons. 8 newtons is more than 6 newtons. That means, hey, friction of 6 newtons is the maximum that can take place here, right? I mean, however, you know, if this was less than 6 newtons, 4 newtons, then the frictional force would have been 4 newtons. But, you know, it has to counter 8 newtons. It can't go all the way to 8 newtons, so it settles for 6 newtons. The difference will be provided by tension, which is 2 newtons. 2 newtons, and therefore the tension on this will be 2 newtons. 2 newtons would be the tension here. Now, realize that this 2 Newton minus 1 Newton, there is a net 1 Newton force acting on it to the right. Now, for it to be in equilibrium, friction of magnitude 1 Newton would have to act here, but can this surface provide the 2 kg block of 1 Newton frictional force? Yes, because it can go all the way to 2 newtons, so 1 Newton is acceptable. So frictional force on this is 1 Newton, frictional force on this is 6 newtons, and the tension in the string is 2 newtons. Thank you so much. Bye-bye. Problem on friction once again. There is a block of mass capital M, and capital M is given to be 50 kgs, and there is small m which is 10 kgs. And the coefficient of friction between small m and capital M is given to be 0.5. And this horizontal surface is smooth. We want to be able to find the minimum value of F. We want to be able to find the minimum value of F so that small m remains held to capital M, so that there is no relative motion between small m and capital M. Hey, if there is no relative motion between small m and capital M, it clearly means they have a common acceleration. So if I look at the free body diagram of small m plus capital M, then in the horizontal direction there is one force acting F, and the acceleration of this is going to be capital F divided by capital M plus small m. That's the common acceleration that the two have. Now, from this acceleration, I can compute the normal reaction between small m and capital M. Why do I need the normal reaction between small m and capital M? So that I can compute maximum static friction between the two. Now, if I look at the free body diagram of capital M alone, there is normal reaction N like this, which is giving it an acceleration A, which is capital F by capital M plus small m. Very clearly, N must be capital M into A. N therefore must be capital M into A, which is F divided by capital M plus small m. Right? So I know the normal reaction. Now, so if the normal reaction between small m and capital M is N, then the maximum static friction between them is going to be mu times N, where N is this, right? Which means now, look, mg is this force acting on it downwards, right? And what can prevent it from falling? Frictional force. So we want friction to balance mg. Right? But realize that the frictional force F is always less than or equal to maximum static friction, which is mu times N, right? That means we have mg less than or equal to 0.5 into N. N is capital M, which is 50, into F, right? I'm replacing N by 50 into F divided by 10 plus 50, which is 60. This is what I get, right? This small m again I replace by 10 kgs. This m I replace by 10 kgs. So then very clearly this goes away, G is 10. So I have like a F greater than or equal to 600. G is 10, 600 by 5 into 0.5, which is like 120 by 0.5, which is like 240 newtons. So F must be greater than or equal to 240 newtons. That means F equal to 240 newtons or more will keep small m held against capital M, and it will not have any relative motion between the two, right? So F larger than or equal to 240 newtons is what we need. So what is the minimum value of F? Minimum value of F must be 240 newtons. Clear? All right. Thank you so much. Bye-bye. There are two masses m1 and m2 in an elevator which is moving up with an acceleration a naught equal to g by 4, right? And the floor of the elevator is smooth, but there is friction between m1 and m2, and the coefficient of friction between m1 and m2 is given to be 1 by 5. There is a horizontal force F acting on m1 whose value is given to be 30 newtons. we want to find the accelerations of m1 and m2 in the elevator frame of reference. That means with respect to the elevator. Do you realize the elevator is a non-inertial frame? It has its own acceleration. So the acceleration of m1 and m2 in the ground frame will be different from the acceleration of m1 and m2 in the elevator frame, right? Surely, if I want to compute everything in the elevator frame, which is a non-inertial or an accelerated frame, then on m1 and m2 I must deploy pseudo forces minus ma0 kind of a thing. So let me write the summary of forces on m1 and m2 in the elevator frame of reference. So in the elevator frame of reference, I will have to put up pseudo forces. This is m2g downwards, and there is m2a0 like this. There is m1g downwards, and there is m1a0 like this, right? This is m2 and this is m1, right? And there is a force F like this, which is given to be 30 newtons. Now, if I look at the free body, see, to compute the maximum static friction between m1 and m2, this is m1, this is m1. If I have to compute the maximum static friction between m2 and m1, I would have to know the normal reaction between them. So what I do is, this is m2. There is like, along with the pseudo force, you have a m2 into g plus a0. Then m1 will exert on m2 a normal force n like this, right? Now, this is summary of forces in the elevator frame of reference. Also, do you realize this F is trying to push m1 in this direction? m1 would want to carry m2 in this direction. So m1 would exert on m2 a frictional force F like this. M1 would try and exert on m2 a frictional force F like this, right? In the vertical direction, m2, m1 have the same acceleration as the elevator. So there is no relative acceleration in this direction for m1 and m2. That means, see, these forces will give me the acceleration in the lift frame. In the lift frame, m2 has no acceleration in the vertical direction. That means with respect to the lift, there is no acceleration of m2 in the vertical direction, which means that the net of all forces, real plus pseudo, in the vertical direction on m2 must be 0, which means n then must actually take care of m2 into g plus a0. This is what must happen, right? Now let me look at m1. So I know the normal reaction, and therefore I also know the maximum static friction. If you like, I can compute that. m2 is going to be what? m2 is going to be 2 kgs into g, which is, so this is g plus g by 4, which is 5g by 4, which is 100 by 4, which is 10, 100 by 4, which is 25 newtons. Is the normal reaction. Therefore, maximum static friction between the two, F max, maximum value of F would be 1/5 of n, mu times n, 25 newtons, which is like 5 newtons is maximum static friction, right? Now let me look at the lower block, which is m1. If I look at the lower block, which is m1, what are the forces acting on m1? Of course, there is m1g downwards and m1a0, because I'm talking about the lift frame of reference. So there is like a m1g plus a0, right? m2 will exert on m1 a normal force n like this, right? And if m1 exerts on m2 a frictional force F like this, m2 will exert on m1 a frictional force F like this, right? Now there is also an additional force, capital F like this, capital F like this, capital F like this, right? Now answer this question. What happens to m1? What happens to m1? When I apply a force F equal to 30 newtons like this, what happens to the frictional force between m1 and m2? Whether there is going to be sliding or not. Whether there is going to be sliding or not. Suppose, so first of all, assume there is no sliding. Assume there is no sliding between M1 and M2. Assume there is no sliding between M1 and M2. Then in the horizontal direction, they must have a common acceleration A. In the horizontal direction, they must have a common acceleration A, which is going to be very clearly F30 divided by, assuming there is no sliding, 30 divided by M1 plus M2. M1 plus M2 is 10. These many meters per second square. 3 meters per second square. Now, let me see. That means, let's see if this common acceleration takes place or not. Right? That means when capital F is 30, then 30 divided by 10, which is the total mass, 3 meters per second square. Now, how much of friction would be required to give M2 a common acceleration of 3 meters per second square? F would be M2 into 3. That means 2 into 3, which is 6 newtons. 6 newtons. Is that possible? M2, which is, sorry, 8. M2, which is 8. I'm sorry, M2, which is 2. 2 into 3, 6 newtons. Can that support? Can that support? Can I have a value of 6 newtons acting on M2? No, because maximum possible value of friction is 5 newtons. Since 6 newtons is not possible, what must have actually happened is a 5 Newton force must, because 6 newtons is not possible. That means they don't reach this value of acceleration. They don't reach this value of acceleration. They can't move with a common acceleration A. F is too large for these to have a common acceleration. For F equal to 30 newtons, if they actually had a common acceleration 30 divided by 10, which is 3 meters per second squared, then the friction required on M2 to give it 3 meters per second squared would have been more than 5 newtons, which is maximum static friction, which is not possible. That means they don't move with a common acceleration. Frictional force, since it can't be 6 newtons, it turns out to be maximum possible, which is 5 newtons. Now, for 5 newtons, what's the acceleration of M2 in this direction? Acceleration of M2 in this direction then is going to be 5 divided by mass of M2. Mass of M2 is given to be 2, which is 2.5 meters per second squared is the acceleration of M2. And what about the acceleration of M1? Look at the acceleration of M1. If I look at M1, this is M1. If M1 exerts on M2 a 5 Newton friction force like this, M2 will exert on M1 a 5 Newton friction force like this. There is capital F. There is capital F, which is given to be how much? 30 newtons. 30 newtons. So net force 25 newtons acting on M1 will give it an acceleration 25 newtons divided by M1. M1 is 8 kgs. So 25 by 8 meters per second squared is the acceleration horizontally. Now, see, in the horizontal direction, the acceleration of the lift is 0 and the acceleration of the particles is A1 and A2. That means these are also relative accelerations with respect to the lift horizontally, because in the horizontal direction the lift has no acceleration. In the vertical direction, all of them bear a common acceleration. So A1 and A2 are relative accelerations of M1 and M2 in the lift frame of reference. Yes or no? In the ground frame, M1 and M2, in addition to having A1 and A2 horizontally, in the ground frame, M1 and M2 will also have an acceleration g by 4 upwards. That means if I look at the ground frame of reference, then in the ground frame, M2, for example, will share a common acceleration g by 4 with the lift, A0, which is g by 4, and will have an acceleration A2 like this. The resultant acceleration would be the resultant of A0 and A2. In the ground frame, therefore, this particle M2, for example, will have acceleration A2 like this, A0 like this, and that means it will seem like having a vertical acceleration A0 and a horizontal acceleration A2, and its net acceleration would be like this, which would be root A2 squared plus A0 squared would be its net acceleration, right? Similarly for M1, as you can see, in the ground frame, there is A0 like this, there is A1 like this, and there is going to be a net acceleration which would be root A1 squared plus A0 squared. But in the lift frame, The lift has A naught upwards, M1 and M2 have A naught upwards. So in the lift frame, M1 and M2 will have simply A1 and A2 as their respective accelerations. Thank you so much. Bye. We have a two-block system. A two-block system pertains to friction. We have a block P of mass 4 kg resting on a block Q of mass 5 kg, and the coefficient of friction between P and Q is given to be 0.2. Q resting on a horizontal surface, and the coefficient of friction between Q and the ground is 0.1. And we need to address some of these questions. Minimum force required to cause the system to move. What's the minimum horizontal force F that will cause the system to move? When F is 4 newtons, what is the acceleration of P and Q? What is the maximum acceleration of the 4 kg block? For what value of F does P start to slip over Q? These are the questions that we need to address. Very clearly, the first thing that you should do in all these problems is, at all the interfaces, you must find the value of maximum static friction. So let me look at the PQ interface. If I look at the P and Q interface, this is P. There is 40 newtons downwards, Mother Earth, and very clearly normal reaction R1 from Q is going to be also 40 newtons. So maximum static friction between P and Q is going to be mu times mu, which is 0.2 into 40, which is 8 newtons. 8 newtons, right? That's between P and Q. Between P and Q, maximum static friction is 8 newtons. Between Q and the ground, again realize, if R prime is the normal reaction from the ground, then R prime must be balancing 9 kg weight. That means R prime must be 90 newtons. 90 newtons, right? So if R prime is 90 newtons, maximum static friction between Q and the ground, realize that R prime from the ground is 90 newtons. It's balancing the total weight, 90 newtons. So F max between Q and the ground is going to be mu, which is 0.1 into 90, which is 9 newtons, right? We have some of this data. This is important. Now, when I pull this 5 kg block, to the right, do you realize that the first thing it has to counter is friction between Q and the ground, and friction between Q and the ground is 9 newtons. Yes or no? That means I have to apply a minimum force F equal to 9 newtons. So part A of the problem, minimum force F that I need to apply must be 9 newtons so that it counters the frictional force between Q and the ground. Maximum static friction is 9 newtons, right? So that's part 1 of the problem. Part B. What happens when F is 4 newtons? When F is 4 newtons, obviously P does not move, Q does not move. Acceleration of both P and Q is 0. And what are the values of frictional force between Q and the ground and P and Q? So for Q and the ground, what's the frictional force between Q and the ground? Q and the ground, if I apply a force F equal to 4 newtons, obviously, you know, friction can counter this because it has the capability to counter up to 9 newtons. So frictional force F is going to be 4 newtons, right? That's Q and the ground. What about P and Q? What's the frictional force between P and Q? Now, look, P doesn't require an acceleration in this direction, because if Q is not moving, P will not move. P does not require any acceleration in this direction. If it does not require any acceleration in this direction, there is no frictional force that Q will exert on P. So if there is no frictional force that P will exert on Q, the frictional force between P and Q will be 0. That's as far as B is concerned, right? What about C? What is the maximum acceleration of the 4 kg block? Now look at the 4 kg block. This is the 4 kg block referred to as P, right? And if I'm driving Q to the right, then friction that Q will exert on P would try to give P the same acceleration to the right, and therefore the frictional force alone is driving P. The frictional force that Q will exert on P is driving P, right? But what's the maximum frictional force that Q can exert on P? The maximum frictional force that Q can exert on P is 8 newtons. So F max that Q can exert on P is 8 newtons. And this will be commensurate with the maximum possible acceleration of the 4 kg block. So the maximum possible acceleration of the 4 kg block is going to be 8 newtons divided by 4 kgs, which is 2 meters per second squared is the max, and that also happens to be the maximum common acceleration of the two blocks, right? Now, so that's part C of the problem, the maximum acceleration of the 4 kg block. For what value of F does P start to slip over Q? Now what really transpires here is the next part of the problem. As I go on increasing capital F, the frictional force between Q and P will go on increasing, right? The frictional force that Q exerts on P, this is P, the frictional force that Q exerts on P so that it could carry P along with it, this will go on increasing, right? So as capital F is increased, small f will also increase initially, and it will, of course, all this starts after I apply F equal to 9 newtons, because up to 9 newtons this will also not have an acceleration. Moment I exceed 9 newtons, this will start having an acceleration to the right, and the frictional force that Q will exert on P will try to give P the same acceleration. Now, very clearly, the maximum common acceleration of the two will happen when Q and P exert maximum frictional forces on each other, which is maximum static friction. See, this is the maximum common acceleration that the two can have. And when the two have a maximum common acceleration of, say, 2 meters per second squared, as we have computed earlier. So if I look at the free body diagram of P and Q, this is P, this is Q, right? And there is a certain value of F for which the maximum common acceleration of 2 meters per second squared happens, and that is the instant when this becomes 2 meters per second squared, the frictional force acting on P will become maximum static, F max, and that's the same frictional force that P will exert on Q, F max, which we have computed maximum static friction between P and Q is 8 newtons, right? This happens when their common acceleration becomes 2 meters per second squared. And when does it happen? This happens for a value of F. If I look at the free body diagram of P and Q together, then this F max is an internal force, and however the frictional force that the ground exerts on Q is an external force, which is 9 newtons. That means F minus 9 must give P and Q, which is 9 kgs, a maximum common acceleration of 2 meters per second square. That means F becomes 18 plus 9, 27 newtons. That means for F equal to 27 newtons, what really happens is the frictional force between P and Q attains its maximum possible value, and that's when P is on the verge of sliding over Q. If I increase F to beyond 27 newtons, the frictional force on P will remain F max, which we have computed to be 8 newtons, and it will continue to move with 2 meters per second squared acceleration, whereas the acceleration of Q will go on increasing, right? So F equal to 27 newtons is the time when P starts to slide over Q, right? They would have attained their maximum common accelerations for a value of F larger than 27 newtons. P will continue to have an acceleration of 2 meters per second squared, whereas Q will have an ever increasing acceleration, and there would be relative motion between the two. Yes or no, right? So this again is an interesting problem. It's not a difficult problem, but it's conceptually relevant. So I hope all of you understand all elements of this problem. Thank you so much. Bye-bye. Again, a very elementary situation. There is a block of mass 1.5 kg resting on a surface, and an external force is applied at time t equal to 0, and it's varying as 1.8 t I cap. I cap means I'm calling this the x direction, right? And its acceleration is 0 for t lying between 0 to 2.85. From t lying from 0 to 2.85, its acceleration is 0. And then for t greater than 2.85, the acceleration of the block is given by 1.2 t minus 2.4 I cap meters per second squared. We want to be able to find the value of coefficient of kinetic friction. Obviously, you know, this is the regime in which kinetic friction comes into play. Because when the acceleration is non-zero, there is kinetic friction, right? And t equal to 2.85 is the transition from static to kinetic. Now, say at a certain instant of time, greater than 2.85, the force acting is this. Kinetic friction would be, well, normal reaction again, as you can see, mg is downwards, and normal reaction, as you can see, will also be mg. So kinetic friction Fk would be mu k mg, would be kinetic friction, and the acceleration when kinetic friction would be given in this direction, right? Which will be given by this line of description. Now, if I have to write equation of motion for the kinetic friction regime, then 1.8 t to the right minus mu k mg minus mu k, which we want to compute. Mg means 1.5 into 10 means 15, equals mass, which is 1.5 into the acceleration at that instant of time in the kinetic friction regime, which is 1.2 t minus 2.4. Yes or no? What we can do is we can, to calculate mu k, plug in t equal to 2.85. Plug in t equal to 2.85 because that's when the transition takes place. You can plug in t equal to 2.85 seconds, which is just the transition from static to kinetic. Put t equal to 2.85, and then the value of mu k that you get would be kinetic friction. Then the value of mu k. So all that you need to do is plug in t equal to 2.85 to obtain the value of mu k, kinetic friction. Sounds good, right? Thank you so much. Bye. We now have a case here. There are two blocks, A and B. A 10 kgs, B 5 kgs, and separated by a very small distance, negligibly small distance, as you can see with these dotted lines. And coefficient of friction between A and the ground and B and the ground is given to be mu s equal to mu k equal to 0.4, right? And block A is pushed by a force that could be varied in magnitude horizontally, F as shown, right? Very clearly, A is held to the ground by means of friction. There is maximum static friction between A and the ground. There is maximum static friction between B and the ground, which is causing welding of A and B with the ground in a certain sense, right? So F max between A and the ground, is going to be mu, which is 0.4 into mg, 0.4 into 100, which is 40 newtons. Between B and the ground is going to be 0.4 into 100, 50, which is going to be 20 newtons, right? So A is held to the ground, and you know, to overcome the friction from the ground, you would have to apply a minimum force of 40 newtons. B is held to the ground, and the welding has strength something to the tune of 20 newtons. That's given in the problem. Now, obviously, for A to be able to press against B, it would have to overcome this frictional force, right? Now, what we want is, we want A to be able to press against B. When will it do that? Obviously, you know, the first thing that F would have to combat is the frictional force between A and the ground, which is a 40 Newton force, right? So if I apply capital F equal to 10 newtons, frictional force acting on A would be to the left 10 newtons. It can go all the way to 40 newtons. When I apply capital F equal to 20 newtons, then ground will exert on A 20 newtons. So the first part of the problem is, but if I apply a force, say 41 newtons, then frictional force will remain 40 newtons, and that 1 newton extra force will be passed on to B, right? Then B will exert on A a frictional force 1 newton like this to keep it in equilibrium, and A will also exert a 1 newton force on B. So now, various parts of the problem. When F is 40 newtons, how much force, with how much force does A press B? With how much force does A press B? So if I apply F equal to 20 newtons, when I apply on A a force F equal to 20 newtons. Is friction capable of countering this? Yes, because maximum static friction is 40 newtons. So frictional force acting on A will be 20 newtons, right? And there is no reason for A to press against B. And then the force between A and B is going to be 0. The force between A and B is going to be 0. Yes or no? So that's first part of the problem. When I apply force F equal to 50 newtons on A, when I apply a force F equal to 50 newtons on A, right, what happens? Frictional force can go only up to 40 newtons. So friction will counter it only to the tune of 40 newtons, right? And then B must exert on A. B must exert on A a 10 Newton force like this, and therefore A must exert on B a 10 Newton force like this. This is what happens. So when F is for 50 newtons, the force between A and B is going to be 10 newtons. So A, like I said, will press B. A, like I said, will press B with a force of 10 newtons. With a force of 10 newtons. And the frictional force that the ground will exert on B will also be 10 newtons. It can go all the way to 20 newtons. So that's good enough, right? So what happens? Frictional force then becomes 10 newtons. When F is 50 newtons, friction force becomes 10 newtons. When F is 60 newtons, suppose when this capital F becomes 60 newtons, this frictional force will remain 40 newtons. B will exert on A 20 newtons like this to keep it in equilibrium. A will then exert 20 newtons on B. A will then exert 20 newtons on B. This way. And frictional force will become 20 newtons. Alright, 20 newtons. Right? But if you apply a force greater than 60 newtons, suppose, so up to 60 newtons, this is what happens. So for F equal to, say, 0 to 40 newtons, what happens? For F equal to 0 to 40 newtons, what happens to the frictional force on B? When capital F just about becomes 40 newtons, just about 40 newtons, frictional force, when this becomes 40 newtons, frictional force on A would have reached its maximum possible value, 40 newtons, and frictional force on B, A has still not been able to touch B. But when F becomes larger than 40 newtons, F becomes larger than 40 newtons, then the difference gets passed on to B, and that difference features in the frictional force. So say, so after F equal to 40 newtons, say now if I apply a force on F on A greater than 40 newtons, on A, if I apply a force F greater than 40 newtons, this frictional force on A will remain 40 newtons, right? What are the forces acting on B? Force acting on B would be the difference. As you can see, force acting on B would be whatever is in addition of 40 newtons. So that's going to be F minus 40. That's going to be, right? And this frictional force will be F minus 40. But only to a certain point. Only to what point? As long as small f does not exceed, this is the frictional force on B, and this should not exceed 20 newtons. 20 newtons. That means for F less than or equal to 60 newtons, the value F minus 40 is FB. So for F less than or equal to 60 newtons, starting from 40 newtons, up to 60 newtons, F less than 60 newtons, from 40 newtons up to 40 newtons, frictional force acting on B is 0, because the whole brunt is borne by A. The static friction between A and the ground manages F up to 40 newtons. 40 newtons onwards, the difference in the force F minus 40 is balanced by the frictional force, but only to the point that F minus 40 does not exceed 20 newtons. That means when F less than or equal to 60 but greater than or equal to 40, what really happens is frictional force on B will be like a F minus 40. F minus 40, right? So it becomes up to 60 newtons, it's going to be F minus 40, right? Now, when capital F becomes 60 newtons, then the frictional force reaches its maximum value, right? And any further increase in F over and above that point will not cause friction to acting on B to increase anymore. So that's how friction acting on B varies with the applied external force capital F. This is what happens. Yes or no? Thank you so much. Bye-bye. In place. Let's look at few more simple problems on friction. So this time we are talking of an inclined plane. We are talking of a fixed inclined plane. This is a fixed inclined plane of angle of inclination theta. And there is a man. Let's say mass of the man is m. And what we want to find is the maximum acceleration with which he can run up the plane and the maximum acceleration with which he can run down the plane so that he doesn't skid or slide on the plane. Maximum acceleration up the plane, maximum acceleration down the plane, that is possible. Given that the coefficient of friction between the man and the inclined plane is mu s, coefficient of static friction is mu s. Now, the idea is really very simple. Suppose if he has to run up the plane, this angle is theta, and he has to run up the plane with an acceleration a. Look at the forces that are acting on it. The forces acting on the man are obviously mg, which could be resolved as mg cos theta perpendicular to the plane, mg sin theta parallel to the plane, and normal reaction n. In this case, it's going to be mg cos theta. N is going to be mg cos theta, right? And the maximum, and what will give him an acceleration in this direction, right? What will give him an acceleration in this direction? Static friction that the plane will exert on the man would be like this. And F minus mg sin theta will give the man an acceleration a. The mass of the man is m, so F minus mg sin theta will be ma. Yes or no? F then becomes m into g sin theta plus a. And this F, in order that there is no sliding between the man and the inclined plane, this F should not exceed maximum static friction, should be less than or equal to mu times n. That means mu times mg cos theta, right? So that gives me like a less than or equal to mu g cos theta minus g sin theta. That's a maximum value of a if he has to go up the plane. Now what if he has to go down the plane? What if he has to go down the plane? If he has to go down the plane with an acceleration a, look, this is theta. Again, like before, n will still be mg cos theta because there is no acceleration perpendicular to the plane. This is mg cos theta this way, then there is mg sin theta this way, and obviously you want friction to support him to get an acceleration a downwards. So if he now wants an acceleration a downwards, you then want friction, so he will push the inclined plane backwards so that the inclined plane exerts on him a static friction F to this in this direction down the plane, and then it is F plus mg sin theta, F plus mg sin theta, which will be m into a, and F then turns out to be ma minus mg sin theta, but F cannot exceed maximum static friction. This F cannot exceed maximum static friction, which is mu times mg cos theta, and therefore you clearly have m getting cancelled, and then we have a less than or equal to g into mu cos theta plus sin theta. So the maximum acceleration down the plane will be this, and maximum acceleration up the plane is going to be this, assuming there is no slipping between his leg, between his foot and the inclined plane, right? So simple problem, but I think it's conceptually relevant and it makes sense. Thank you so much, but more to come. Bye-bye. Basic conceptual situation. There is a block of mass small m resting on a trolley of mass capital M, and the trolley is moving on a smooth horizontal surface, right? And there is friction between small m and capital M, right? And there are two situations. A horizontal force capital F is applied on small m, and a horizontal force capital F is applied on capital M. And what's given is that there is no relative motion. There is no relative motion between small m and capital M. There is no relative motion between small m and capital M. We want to find the frictional force between small m and capital M. We want to be able to find frictional force between small m and capital M. Now, realize one thing. If there is, look at case 1. If there is no relative motion between small m and capital M, then they have a common acceleration a to the right. They have a common acceleration a to the right. And if they have a common acceleration a to the right, then if I look at the free body diagram of small m plus capital M, then of course, whatever forces they exert on each other, friction as well as normal, would be internal. There is Mother Earth which is acting downwards, and there is normal reaction from the ground acting on the trolley. But then in the horizontal direction, the common acceleration A then would be given by capital F divided by capital M plus small m. That's a common acceleration. Now, agreed, small m is being acted upon by capital F, and there is frictional force between small m and capital M, right? But what about capital M? Who's driving capital M? How is capital M getting its acceleration a to the right? Look at capital M. Look at capital M. Capital M, realize, has a common acceleration A, and therefore there must be a horizontal force acting on capital M, and that would be the frictional force that small m exerts on capital M. Static friction, because there is no relative sliding between small m and capital M. There is static friction F that small m will exert on capital M, so that it could give capital M an acceleration A to the right. Yes or no? So this small f must be capital M into A, capital M into A, which is like capital M into A that we have found is capital F by capital M plus small m, right? So that's the value of the frictional force. Obviously, you know, this frictional force cannot exceed maximum static friction, which will be less than or equal to mu times small mg. If you have to draw the free body diagram of small m, free body diagram of small m will be this. Small m is like this. There is capital F acting on it this way. And if small m exerts on capital M a frictional force F to the right, capital M will exert on small m an equal and opposite frictional force F to the left, under the influence of which it will have a common acceleration A to the right. Right? From here also you can say capital F minus small f is m into A, and you would get the same value of small f. You know, you could have said capital F minus small f is small m into A, and you could have got small f as capital F minus m into A, which is A is capital F divided by capital M plus small m, which will give you the same value of the frictional force, which will give you the same value of the frictional force. Yes or no? Now, the situation is now slightly modified. I apply a horizontal force capital F acting on capital M, and they move with a common acceleration A to the right. If they move with a common acceleration A to the right, which means now if I have to draw the free body diagram of small m plus capital M, from this I can get A equal to F divided by capital M plus small m is what I'll get. Yes or no? And realize that what drives small m? How is small m getting its acceleration A to the right? Small m is getting its acceleration A to the right, or common acceleration with capital M. Common acceleration with capital M, because capital M is exerting frictional force, and this time static friction. Why? Why static friction? Because there is no relative sliding between small m and capital M. Then this small f would be m into A that we have found is capital F by capital M plus small m. Yes or no? Now, another important thing that you might just want to quickly take notice of, if you're done with this, can I wipe this off? Right, let me explain another very relevant, very pertinent situation in the context of all of this. Look, suppose there is a block of mass small m, and there is say a block of mass capital M, right? And let's say the coefficient of friction between small m and capital M is mu. And if I apply a force capital F to capital M, if I apply a force capital F to capital M, then what would happen to small m? What would happen to small m? Small m will be acted upon by frictional force to the right. Capital M will exert on small m. Capital F will exert on small m a frictional force F to the right, because frictional force will try to do its bit so that capital M and small m are in sync, so that they move together. That's why, if capital M is moving to the right, it's not selfish enough if it exerts on small m a frictional force F to the right, so that small m could also perhaps move with the same acceleration as capital M to the right. But realize that the value of this small f can be anywhere from 0 to maximum static friction. Now, what is the maximum static friction between small m and capital M? Look at this. This is small m. The normal reaction that capital M will exert on small m will be equal to the weight. Why? Because there is no vertical acceleration. So mg acting downwards, normal reaction in this case is acting upwards. And therefore, the maximum static friction F max would be mu n, which is mu mg, right? Which means this F cannot exceed mu mg. Mu is the coefficient of static friction between small m and capital M. And if this has an acceleration a because of small f, then small f would be m into a. Small f would be m into a. This is less than or equal to mu mg. That means a cannot exceed mu g. A cannot exceed mu g. That means the maximum possible acceleration of the upper block is going to be mu g. That means if the coefficient of friction is 0.2, then the maximum acceleration of this upper block, is going to be mu into g, which is 0.2, let's say, into g is 10 meters per second square. That means the maximum possible acceleration of the upper block, which is driven by friction alone, can be 2 meters per second square, right? And similarly, if I have a system like this, and say this is smooth, this is small m and this is capital M, right? And mu is the coefficient of friction between small m and capital M. And if I apply a force, say this is smooth, all right? And if I apply a force capital F on it like this, then once again, irrespective of what force I apply, the maximum static friction between small m and capital M will still be mu mg. F max between small m and capital M will still be mu mg. Right? That means now what would small m do to capital M? It would want capital M to move along with it. Therefore, if this fellow is trying to move to the right, it will exert on capital M a rightward frictional force, so that small m and capital M could move in tandem together. That means now the frictional force acting on capital M would be to the right. Right? And if it would be to the right, realize that it will have an acceleration a to the right. And this F cannot exceed mu mg. And if it has an acceleration a to the right, the lower block, which is driven by friction alone, then capital M into a is less than or equal to mu mg. That means the maximum acceleration a less than or equal to mu mg divided by capital M. That means the maximum acceleration of the lower block is going to be mu mg by capital M. Yes or no? Thank you so much. Bye-bye. Friction. A situation that I present again, not difficult, but again pertinent. There is a block of mass m, and this is a vertical wall. And the coefficient of friction between small m and the vertical wall is mu s. Alright. At an angle theta, I apply a force F like this. At an angle theta with the vertical, I apply a force F like this. I want to find the minimum value of F. I want to find the minimum value of F so that small m doesn't slide. This is what I want, right? So clearly, this guy has weight acting downwards, and there is like a F cos theta acting upwards and F sine theta acting downwards. F sine theta acting downwards. I'm assuming that F cos theta is less than mg so that it has a net tendency to slide. Let me take the case where F cos theta is less than mg so that it has a tendency to slide and that friction will act on it upwards. So that friction will act on it upwards. Very clearly, the normal reaction that the wall will exert on small m will just about balance F sine theta. N will just about balance mg F sine theta. And F must balance mg. F must balance mg. But F cannot exceed maximum static friction mu times n. That means mg less than or equal to mu times n, which is F sine theta. F sine theta, right? So, I'm sorry, F, in fact, I'll fix this. There is a mistake that I made here. The mistake is we must have F cos theta plus small f. F cos theta plus small f. That must balance mg. That's a mistake I made, right? F cos theta plus small f must balance mg. That means F must be equal to mg minus capital F cos theta, right? But F cannot exceed maximum static friction, so it's going to be less than or equal to mu times n. N very clearly is F sine theta. And now I transpose this on this side, I get F into mu sine theta plus cos theta. By transposing this on this side, greater than or equal to mg. So we very clearly have F greater than or equal to mg by mu sine theta plus cos theta. So that's the minimum value of F that I must apply so that I can keep it pressed against the wall. So that I could keep it pressed against the wall. Now there could also have been a situation. So this is if F cos theta is less than mg, it has a tendency to slide down. But what if F cos theta is greater than mg? Then it has a tendency to slide up. So there is like F cos theta upwards, and there is of course F sine theta in this direction, and then of course we have normal reaction N from the wall like this. There is mg this way. Very clearly, if F cos theta is greater than mg, it will have a tendency to move up. If it has a tendency to move up, obviously frictional force on it will act downwards. So this is a case where F cos theta is greater than mg for a certain F and theta. And N, of course, once again will be same F sine theta. And now for equilibrium, what is required? F cos theta must take care of mg plus small f, right? That means small f is like a capital F cos theta minus mg, as you can see. But small f cannot exceed maximum static friction, so this must be less than or equal to mu times n. N is F sine theta, right? So this is like F transposed on this side, cos theta minus mu sine theta less than or equal to mg. That means F less than or equal to mg by cos theta minus mu sine theta, right? So the maximum value of F that you want to apply is this. This is the minimum value of F that you want to apply so that it remains in equilibrium against the wall. So the range of F, you know, if you lie within this range, if you go smaller than this, if you go smaller than this, or if you go larger than this, it'll slide against the wall. But if you are greater than this and less than this, it'll stick to the wall. Thank you so much. Bye. Take to this situation. What is the situation all about? There is a table and a block of mass capital M rests on it. It's rough. It's a rough table. And there is a thread passing over a smooth pulley and with the mass small m hanging as shown. What we want to find is, so we are assuming that this pulley is smooth. There is no friction, ideal pulley otherwise. We want to find the tension in the string. Now that's easy, because if capital M is stationary, that's given in the problem, small m will also be stationary. So if this is T, T must take care of mg very clearly. So I know T must be mg. That's 1. 2. If I look at the free body diagram of capital M, there is T acting this way. Of course, you know, there is capital mg like this, and there is normal reaction R from the ground like this. But capital M is also stationary. That means frictional force F acting on it must be in this direction, and F must just balance T. So F must just balance T, which is found to be mg. So I know the frictional force acting on capital M, that must be mg. Now the force that the thread exerts or the string exerts on the pulley. So let me just draw the free body diagram of the pulley. There is like a T like this, there is T like this, there is T like this. Evidently this T and this T, there is a T which is horizontal, there is a T which is vertical, and the resultant of the two T's is T root 2 like this, is like a T root 2 this way. So the net force that the string exerts on the pulley is T root 2, and obviously you can see it will make an angle 45 degrees as shown. T root 2 means mg root 2 in this direction. Sounds good, right? Okay, so let's move on to some more simple situations. Thank you. Bye. Situation that I want to deal with. There is an inclined plane of angle of inclination theta. There is a block of mass small m resting on the inclined plane, and you want to give inclined plane an acceleration a to the right. What should be the value of the frictional force so that there is no relative motion between the inclined plane and the block m? Right? The inclined plane is given an acceleration a to the right. What should be the frictional force between small m and the inclined plane so that it has an acceleration a to the right, same as that of the plane? See, I don't want any relative motion between small m and the inclined plane. So if the inclined plane has an acceleration a to the right, I want small m also to have the same acceleration a to the right in order to prevent relative motion. So now, what are the forces? Realize that this angle is theta. Along the plane, then small m should have an acceleration a cos theta, and perpendicular to the plane, it must have an acceleration a sin theta, right? And the forces acting parallel to the plane are like, as you can see, as you might have seen so many times in the past, mg sin theta, component of mg in this direction, and say frictional force F in this direction, right? Now, writing equation of motion in this direction, I have like a mg sin theta minus F, mg sin theta minus F, that must give small m an acceleration a cos theta in this direction, m into a cos theta, right? So that gives me F equal to m into g sin theta minus a cos theta upwards, right? Clear? Now suppose I want to give the inclined plane an acceleration a to the left instead. I want to give the inclined plane an acceleration a to the left, and I want no relative motion between small m and the inclined plane. What should be the value of the frictional force between small m and the inclined plane? Now what are the forces acting on small m? Of course, you know, first of all, one must understand that small m must also have the same acceleration a to the left as the inclined plane, so that there is no relative motion between the two. So if this is theta, you would expect this to be theta, right? And then its acceleration perpendicular to the plane is a sin theta, acceleration of small m parallel to the plane is a cos theta, right? And look, this is like mg sin theta, this is like mg sin theta this way, this is mg sin theta this way. And what about the frictional force? What about the frictional force, right? Frictional force, let's say, will act upwards, to get it an acceleration a cos theta like this. So we then have F equal to F minus mg sin theta, F minus mg sin theta is m a cos theta. So that gives me F equal to m into g sine theta plus a cos theta. G sine theta plus a cos theta, that's the value of the frictional force, and in a direction shown. Yes or no? Right? So in this case, it is m into g sine theta minus a cos theta. In this case, it's f upwards m into g sine theta plus a cos theta. That's what happens. Thank you so much. Bye. Really simple situation. There is a block of mass capital M, and there is a mass small m which rests against the vertical wall. I want to find the minimum value of A so that small m has no relative motion with respect to capital M. Realize that if small m has to remain in contact with capital M, then the only perceptible relative motion would be along the wall, along the vertical wall, right? And we don't want that to happen, right? That means we want small m and capital M to have a common acceleration a to the right, and if the acceleration of small m is a to the right, what can give small m an acceleration a to the right? There is a normal reaction that capital M exerts on small m, which is n, that will give small m an acceleration a to the right, and therefore would be m into a. So I know the normal reaction between small m and the block. Now, realize that it has a tendency to slide down, right? And therefore, to prevent it, friction will act upwards. Friction will then be equal to mg, but it can't exceed maximum static friction. That means it can't be great, it has to be less than or equal to mu times n. That means mg has to be less than or equal to mu times n. N, as we have seen, is mg, ma from this equation. So we have a greater than or equal to mu g. So if you impart this block by some means an acceleration a to the right greater than or equal to mu g, then there would be no relative motion between small m and capital M. They will enjoy a common acceleration a to the right. Thank you so much. Bye. There is a pulley system connected to a mass m3 hanging vertically as shown. There is a block of mass m2 resting on the surface with coefficient of friction mu s, and m1 resting on top of it, and there is a string which connects it to m3, right? We want to be able to comment on m3 so that m3 does not move, What should be the range of m3, values of m3, so that m3 does not move? Now, if m3 does not move, m2 will not move, and therefore m1 will not move. Yes or no? And if T is the tension in the string, then T must very clearly balance m3g. So I know the tension in the string, that's balancing m3g, right? Now, look at the free body diagram of m1 plus m2. There is T like this, and there is frictional force F acting between m2 and the ground, which is like this. And very clearly, the normal reaction that the ground will exert on m2 will just about, if I look at the free body diagram of m1 plus m2, this n will balance m1 plus m2 into g. Now, that will give me, so one thing, F must be equal to T. F must be equal to T for equilibrium of this, and this F cannot exceed maximum static friction, must be less than or equal to mu times n. Mu times n means m1 plus m2 into g, right? That means, what is T? T, as you can see, is m3g. m3g less than or equal to mu times m1 plus m2 into g. Therefore, m3 cannot exceed mu times m1 plus m2. That means that there is a greatest value of m3, which is like mu times m1 plus m2, for which the whole unit will be stationary fixed. Yes or no? Pretty simple. Thank you so much. There is an arrangement of this kind. m1 and m2, there is friction. Coefficient of friction is mu s, and this surface is smooth. And m3 is hanging vertically like this. Now, coefficient of friction between m1 and m2 is given to be mu s. I want to be able to find the greatest value of m3 so that there is no relative motion between m1 and m2. Now, again, if there is no relative motion between m1 and m2, say if T is the tension, there is m3g acting like this, and this has an acceleration a downwards, whereas this whole unit, if there is no sliding between m1 and m2, this whole unit has an acceleration a to the right, right? Now, if I apply Newton's second law to this, I get like a m3g minus T is M3A. I can find A. And if I apply Newton's second law to this system, M1 plus M2 together, then frictional force and normal reaction between these two would be internal forces. Then T would be M1 plus M2 into A. And if I add these two, then I get the value of A. A very clearly turns out to be M3G divided by M1 plus M2 plus M3. That's the common acceleration, right? Now, once I have this in place, what supports M2? So first of all, let's find the maximum frictional force between M2 and M1. Realize there is M2G acting downwards. If I look at the free body diagram of this, there is normal reaction N from the ground from M1 acting upwards. N very clearly is M2G. Now, how does M2 get its acceleration A to the right? Same as the acceleration of M1. It's M1 will exert a frictional force F on M2, static friction, because there is no sliding between M1 and M2. F is the static friction that M1 exerts on M2, so that there is no relative motion between M1 and M2, and they could move with the common acceleration A. Now, so if this has an acceleration A, realize that this F must be providing M2 an acceleration A, but F cannot exceed maximum static friction, mu times M2G. And that, like before, gives me A, the maximum acceleration of M2, which is also the maximum common acceleration between M1 and M2, cannot exceed mu G, which is a result I want you to anyways remember. A cannot exceed mu G if there has to be no relative motion between M1 and M2. That means the maximum acceleration that M2 get because of its feed from M1 in the form of friction is mu G. And what is A? A, as you can see, is like, as we've obtained, M3G divided by M1 plus M2 plus M3 cannot exceed mu G, or we then have M3 less than or equal to mu into M1 plus M2 plus M3 divided by M3 divided, this is it. M3 less, okay, I still have to solve for M3. I cross multiply, I get this, or then I get like a M3 into 1 minus mu has to be less than or equal to mu into M1 plus M2, and therefore I get M3 less than or equal to mu into M1 plus M2 divided by 1 minus mu. This is what happens, right? So the greatest value of M3, would be this number, I transpose mu M3 on this side, and this is what transpires. Yes or no? Thank you so much. Bye-bye. Additional situations for a brief discussion. We have a system like this. There is M1 resting on a surface where the coefficient of friction is mu, and passing over a smooth pulley, and there is an arrangement like this. This is mass M2, and there is a rope fixed at this end, string fixed at this end, light inextensible string. Now in this situation, we want to find the maximum possible value of M2. We want to find the maximum possible value of M2 so that M1 does not slide on the ground. Now, simple. Realize that if T is the tension in the string, then this T and this T will balance, 2T will balance M2G. M2G. Yes or no? That means T is obviously M2G by 2. And this T, for it to not slide, see, what is the maximum static friction between M1 and the ground? Maximum, this is the frictional force F acting on it like this, and T should be equal to F. T should be equal to F. T should be equal to F, but F cannot exceed maximum static friction between M1 and the ground, which is like a mu M1G, right? That means M2 from this and this, M2 less than or equal to 2 mu M1, 2 mu M1. Yes or no? That means M2, greatest value of M2 is 2 mu M1, cannot exceed this value. Yes or no? And when M2 becomes equal to 2 mu M1, this frictional force assumes its maximum static value. So that's for this situation. Let's refer to this situation. Again, I want to find the maximum possible value of M2 so that this doesn't M1 doesn't slide on the horizontal surface. So one thing, the tension in this string, say T1, must balance M2G. So T1, I know the tension in this string. T1 therefore must be M2G. Now if I look at the free body diagram of M3, there is like a M3G acting this way, right? There is T1 this way, and there is also T1 this way, right? On this, there is T1 this way. And there is no acceleration of this M3. So the tension here, T, must be equal to what? 2T1 plus M3G? T must be 2T1 plus M3G, right? Where T1 we know is M2G. T1 we know is M2G. So T is 2T1 plus M3G. So I know the tension T here. T is 2T1. 2T1 means 2M2G plus M3G. 2M2G plus M3G. That's T. That's T. Now, that's also the T acting here. And this T should not exceed the maximum static friction between M1 and the ground so that M1 stays still. So then what we must necessarily have is T less than or equal to mu M1G. Because if T, the external force acting on M1 is not exceeding maximum static friction, it will stay put on the ground. T, which is like 2M2G, T we have obtained as 2M2G plus M3G less than or equal to mu M1G. G of course will get cancelled. Then we have 2M2 less than or equal to mu M1 minus M3, or M2 not exceeding mu M1 minus M3 by 2. So this is the greatest value of M2 for which M1 will not slide on the ground. Yes or no? Thank you so much. Bye-bye. Check this situation. There is a block of mass M1 resting on another block of mass M2 which rests on the floor. And there is coefficient of static friction between M1 and M2 mu, and M2 in the ground also as mu. And you know, this is fixed to the wall. This is fixed to the wall like this, right? We want to find the minimum value of F. We want to find the minimum value of F so that M2 can move on the ground, so that M2 could move on the ground. Now, realize that clearly there is going to be relative motion between M1 and M2. Yes or no? Because M1 is not moving to the right because of this string, right? It's holding on to the wall. Whereas M2 is moving to the right. So if M2 is moving to the right, M1 will exert on M2 a frictional force to the left. Yes or no? So look at M2. Look at M2. M2. M1 will exert, right? Because the relative motion of M2 with respect to M1 is rightwards. So M1 is not liking the situation that M2 is moving away from it. So M1 would want to drag it towards itself. Now since M1 can't move, so M1 says, all right, let me at least exert a frictional force on M2 like this. And there is relative motion. That means the frictional force between M1 and M2 would have reached its maximum static value. And realize that the normal reaction between M1 and M2 is M1G. Therefore, maximum static friction between M1 and M2 is going to be mu M1G. So this frictional force F1 is going to be mu M1G. Is going to be mu M1G. Right? And M2 is sliding on the ground. So there is going to be frictional force mu M1 plus M2 into G. Why? Why? Because the normal reaction between the ground and M2 is M2 plus M1G. If I had to look at the free body diagram of M1 and M2 together, then in the vertical direction, the net force M1 plus M2G because of Mother Earth must be balanced by normal reaction from the ground, M1 plus M2 into G. So then the frictional force between the ground and M2 is going to be mu into M2 plus M1 into G. Now very clearly, in order that M2 moves to the right, F must be larger than or equal to F1 plus F2. Yes or no? F has to overcome this friction as well as this friction. So F has to be greater than, in order that it could move to the right, F has to be greater than or equal to mu M1G plus mu M1 plus M2 into G. right? That means F has to be greater than or equal to, if I take mu G common from this, so that's like a 2m1 plus m2. That means what is the minimum value of F for it to slide on the ground? Minimum value of F must be mu G into 2m1 plus m2. That's the minimum value of F. Yes or no? It makes sense to all of you? Let's proceed. Thanks. Bye. So we have two blocks, m1 and m2. m1 resting on top of m2, m2 on a ground, and coefficient of static friction between m2 and the ground is mu, and the coefficient of static friction between m1 and m2 is also mu. And there is a string that connects m1 and m2 passing over a smooth frictionless pulley which is fixed to the wall. I want to find the minimum value of F so that I could move m2. We want to be able to find the minimum value of F so that we could move m2 to the right. Now, one thing for sure, you know, if m2 moves to the right with a certain acceleration a, then because of the string consideration, that means if this length of the string increases by a, this will decrease by a. That means m1 must move to the left with the same acceleration a, right? Now, the maximum static friction between m1 and m2 is like mu m1g. I hope all of you realize this by this time, because the normal reaction that m2 will exert on m1 would be upwards n, which will balance m1g. So this is maximum static friction F max between m1 and m2, right? And maximum static friction between m2 and the ground, realize normal reaction from the ground is going to be m1 into plus m2 into g. So maximum static friction between m2 and the ground is going to be mu times m1 plus m2 into g. Now, look at m2. Let's look at the free body diagram of m2. m2. What are the forces acting on m2? What are the forces acting on m2? There is, of course, you know, in addition to there is weight which is acting downwards, There is normal reaction from the ground, which is m1 plus m2 into g acting upwards. There is tension T acting this way. There is capital F acting this way, right? There is capital F acting this way. And between m2 and the ground, since there is actual relative motion between the two, frictional force between m2 and the ground would have reached its maximum value, mu into m1 plus m2 into g. Since m2 has a tendency to move to the right, frictional force, which would have just about reached its maximum static value, is going to be mu into m1 plus m2 into g. That's as far as m2 is concerned. That's not all. Realize that m2 is moving to the right, right? So relative motion of m2 with respect to m1 is rightwards. m1 thinks that m2 is moving to the right, so m1 will exert on m2 a frictional force to the left, and realize there is actual relative motion between m1 and m2, so friction would have reached its maximum static value, and the maximum static value is mu m1g. So there is mu m1g acting this way, right? Also, look at the free body diagram of m1. Look at the free body diagram of m1. What all is happening to m1? There is tension T like this. There is tension T like this, right? And if m1 exerts on m2 a frictional force mu m1g like this, m2 will exert on m1 a mu m1g this way, right? After all, you know, m2 is generous, benevolent. It would exert frictional force on m1 in the same direction in which it is moving because it wants it to move with it, right? Mu m1g. And the net effect of all of this on m1 is an acceleration a. Now, so this has an acceleration a, f minus t minus mu g into 2m1 plus m2 I'm writing equation of motion of this is M2A, M2A. Yes or no? F minus T minus mu M1G minus this is M2A, right? And what about T? T, as you can see, T minus mu M1G is M1A, right? So I can replace T by mu M1G plus M1A. So F minus T, T can be replaced by mu M1G plus M1A minus mu G into 2M1 plus M2 is M2A, right? F therefore, as you can see, is like a mu G into 3M1 plus M2, combine these two, and then there is M1A, M1 plus M2 into A, M2 into A, right? Now we want to find the minimum value of F. Minimum value of F when this acceleration is very small, when this acceleration is 0, very close to 0, when this acceleration is just about 0, then you get F minimum, right? Since this is greater than or equal to 0, right? Because A is to the right and positive. Since this is greater than or equal to 0, this number, this plus this has to be greater than this, is therefore greater than mu G into 3M1 plus M2. So what is F minimum? F minimum is mu G into 3M1 plus M2. 3M1 plus M2 is F minimum, right? So any value of, so when F reaches this value, then frictional force between M2 and the ground will become maximum static, between M1 and M2 will become maximum static, and everything would be on the verge of sliding. F just larger than this will begin to have an acceleration, certain acceleration A to the right, this will have the same acceleration A to the left. But then what's the smallest value of F that you must apply? That must be equal to this. Yes or no? Right? So this brings us to yet another problem that makes sense. We'll see you in a while. Bye. Here we have a system in which capital M is connected to M2 by a light inextensible string passing over a smooth light pulley, and is also connected to M1 by means of a string passing over a smooth light pulley connected to a mass M1. What we want to deal with is we want to be able to, and there is friction between capital M and this surface, and the coefficient of static friction is mu. And M1 is fixed and we have control over, suppose M1 is fixed. But M2 could be varied, say M2 could be varied. Now, we want to be able to comment on M2 so that capital M does not move, right? These are two things that we want to know. So, one thing, if capital M is not moving, neither M1 nor M2 will move, right? So, if I look at tension in this string as T1, then what would this T1 do? This T1 would just about balance M1G. So I know this T1 is M1G, right? If I look at tension in this string as T2, then this T2 will balance M2G. T2 is M2G, right? Now if I look at capital M, there is tension T2 acting this way, there is tension T1 acting this way, right? Very clearly, if T1 is equal to T2, which will happen if M1 equal to M2, capital M will not have any tendency to slide on the ground, right? But case 1, where say T2 is more than T1, if T2 is more than T1, then capital M has a tendency to slide to the right. T2 is more than T1. This is more than this. Then if you look at capital M then has a tendency to slide to the left, and frictional force F will act on it leftwards. And this frictional force must just balance T2 minus T1. right? So frictional force will be of value T2 minus T1. T2 minus T1 means M2 minus M1G. And that should not exceed maximum static friction. Maximum static friction between capital M and the ground is like mu capital Mg. Mu capital Mg. So very clearly, T2, which is M2 minus M1 into G, is less than or equal to mu capital Mg, right? Or we have M2, G getting cancelled, M2 less than or equal to mu M plus M1. That's one thing. That is if T2 more than T1, that means if M2 is more than M1. So the other possibility is T2 less than T1. T2 will be less than T1 if M2 is less than M1. If M2 is less than M1. Right? If M2 is less than M1, then T2 will be less than T2. If T2 is less than T1, if T2 is less than T1, that means the net force on this is going to be T1 minus T2 to the left because of the tension. It will have a tendency to move to the left. Frictional force F will act on it to the right. And then we have T1 minus T2 taking care of friction. But the maximum static friction, small f, between capital M and this cannot exceed mu mg. Maximum static friction cannot exceed mu mg. So T1 minus T2, T1 is M1 minus M2 into G, less than or equal to Q mg, or we have like M2 greater than or equal to M1 minus mu m. Right? These are the two possibilities. I hope it makes sense. So these are two things that we can say about M2 if I want capital M to be at rest. Thanks so much. Bye. We have a truck moving to the right with an acceleration A, and there is a sandbag of mass 75 kgs resting on the truck. And there is coefficient of friction between the sandbag and the truck given to be as mu. We want to find the maximum possible value of A so that the sandbag does not slide on the truck. There is no relative motion between the sandbag and the truck. Now, one thing, if you want no relative motion between the sandbag and the truck, this is the sandbag of mass M. The sandbag should have an acceleration A to the right. And who will give the sandbag this acceleration? The frictional force that the truck will exert on the sandbag, which must be F. That F must be M into A. Right? But this F cannot exceed maximum static friction between M and this. That means this cannot exceed mu mg. That means A, acceleration of the truck, has to be less than or equal to mu g so that there is no relative motion between the sandbag and the truck. That means A has to be less than or equal to, suppose somebody gave you mu as 0.2 or say 0.2, then say A would be 2 meters per second squared if mu is 0.2, for example. So one way or the other, the maximum acceleration, or in fact even the maximum retardation of the truck that will prevent relative motion between the sandbag and the truck is mu times g. So A in magnitude should not exceed mu g to prevent relative motion between the sandbag and the truck, right? So I hope I've gotten you past almost a large number of very basic simple illustrations, right? And I hope all of it makes sense to you. But I'm still not done. I'm hell-bent on making sure that you understand every aspect of friction. But this much for today. Thanks a lot. Here we have a hemisphere, fixed hemisphere, hemispherical bowl, and there is a particle of mass m. And the coefficient of friction between this particle and the hemispherical bowl is given to be 1 by root 3. Now we want to find out the radius of the hemisphere is r. We want to find out the maximum height at which the particle can be placed on the inner surface of the hemisphere so that it doesn't slide down. As you keep raising the particle to greater and greater heights, its propensity to fall down, slide down, increases. The question is, what's the greatest height edge to which you can raise it so that it doesn't fall off the surface, it doesn't slide down the surface, right? Now, obviously, the greatest height to which this reaches would be, let's say, located by an angle theta that the radius makes with the vertical. What are the forces acting on the particle m? And it's given that mu s is 1 by root 3. Say mu s is 1 by root 3. Now in general, at an angle theta, when the particle is still in equilibrium, in general, what are the forces acting on it? There is mg like this. There is normal reaction that the surface exerts on the particle, which goes through the center. And if this is theta, obviously, you know, this angle is also theta. And if this is theta, see, the normal is perpendicular to the tangent. The normal will always be perpendicular to the tangent, right? Again, as you can see, this is 90 minus theta. So this line, tangent, is perpendicular to the normal. This is 90 minus theta, so this will be theta. So the tangent will make an angle theta with the horizontal, right? Now, realize that it has a tendency to fall down because there is mg sine theta acting this way, which causes it. And what prevents it from sliding down? There is frictional force, static friction F, acting upwards, opposing mg sine theta along the tangent, which prevents it from sliding. Now, realize that for equilibrium in this position, the vertical component of F and N must balance mg. That means F sine theta. As you can see, vertical component, this is theta, this is 90 minus theta. Of course, as you can see, this is theta. So F sine theta plus N cos theta must balance mg. Must balance mg, right? Also, the horizontal components of F and N will cancel off. That means F cos theta must cancel off N sine theta. This is what must happen, right? And since F is always less than or equal to mu n, since F is always less than or equal to mu n, so F cos theta will always be less than or equal to mu n cos theta. See, F less than or equal to mu n, so F cos theta will always be less than or equal to mu n cos theta. That means theta must be such, for equilibrium, theta must be such that tan theta must always be less than or equal to mu. That means tan theta must be less than or equal to mu, which is 1 by root 3. That means maximum value of theta is 30 degrees. Pi by 6, that's the maximum value of theta, 30 degrees. That means when this becomes maximum, the height h becomes maximum. That means when this theta becomes 30 degrees, h becomes h max. So when theta is 30 degrees, h will be h max. And I need to calculate h max. Right? To calculate h max, all that you need to do is, this is r, this length is r, and this is r, so this length is going to be r cos theta, as you can see, because this is r, so this is going to be r cos theta, and this is going to be r minus r cos theta. This is r, so this is going to be r minus r cos theta, r into 1 minus cos theta, and that's going to be h max, h max, for theta equal to 30 degrees. So this is r into 1 minus cos 30 degrees. That means this is r into 1 minus root 3 by 2. That's the maximum possible value of h to which you can raise it so that it doesn't slip off the ground. If you try to raise it any further, the mg sine theta will increase, but frictional force will remain the same, and it'll slide down the sphere, right? So the other way you could have looked at this problem is that, you know, this, what we have learnt in the past is that if there is an fixed inclined plane, right, of angle theta, and if there is a particle of mass m, and the coefficient of friction between the particle and this fixed inclined plane is mu s, then the value of theta for which the particle m will not slide down the plane must satisfy this, tan theta less than or equal to mu s. Then the particle will not. That means the maximum value of theta for which it will not slide down the plane would be given by tan theta equal to mu s is the maximum value of theta for which it will not slide down the plane. Values of theta larger than the ones given by this equation, it will slide down the plane. Values of theta smaller than the theta obtained from this equation, it will not slide down the plane. So that means this is the limiting theta for which it will not slide down the plane. Don't try to increase theta beyond this, otherwise it will fall off. Now the hemisphere could also be looked upon as an inclined plane where theta is different at different points, right? It's an inclined plane of variable theta. The surface of the hemisphere is an inclined plane of variable theta, So very clearly, what's the limiting theta we are looking at? We are looking at the limiting theta, because see, this is like a tangent making an angle theta. So this point could have been looked upon, mentally perceived to be an inclined plane with angle of inclination theta, right? And you don't want theta to be such that tan theta is greater than mu s. You want tan theta to be smaller than or equal to mu s, and therefore the greatest value of theta would be given by tan theta equal to mu s to prevent the particle from sliding down the plane. So tan theta equal to mu s means 1 by root 3 theta would have been 30 degrees. So you could have looked upon this hemisphere as a variable inclined plane with variable theta, and the limiting theta would be given by tan theta equal to mu s. Thank you so much. We are through with a lot of fundamentals in friction. I thought I'll add a very interesting layer in terms of problem solving across to you. The next situation which I'm going to discuss with you is something that I really enjoy, and I really like this situation. It drives home a world of wisdom related to friction. Let me tell you what this situation is. This situation is about a belt horizontally moving with a speed of 3 meters per second. It's moving with a speed of 3 meters per second, let's say along the x-axis, right? There is obviously a motored mechanism that causes it to move. Now, what is done is, there is a particle of mass m. There is a particle of mass m which is launched with a velocity of 4 meters per second in a direction perpendicular to the motion of the belt. Let me call this the y-axis, which is perpendicular to the x-axis. Along the belt, it's launched with a velocity of 4 meters per second in a ground frame perpendicular to the x-axis, right? This is the velocity of the particle m in a frame attached to the ground. The belt has a certain width. This is the width of the belt. Along the y-axis, the dimension is the width of the belt. The belt is not smooth. There is friction between the particle and the belt. And the coefficient of friction between the particle and the belt is given to be 0.5. So now there are a few things that I want to analyze here. First of all, in a frame of reference attached to the belt, what would be the trajectory of this particle m? In a frame of reference attached to the belt, what would be the trajectory of this particle? 1. 2. What is the minimum width so that this particle doesn't fall off the belt? Obviously, if you give it a very high velocity, it'll overshoot this mark and it'll fall off the belt. And then during this journey, what is the minimum velocity of the particle in a ground frame, right? So first things first, a few very basic things that I want you to very clearly comprehend. One is that eventually realize that the velocity of the particle is along the y-axis. Let me draw a different figure for you. This is the x-axis along which the belt is moving. This is the y-axis. This is the belt, which is like this, right? The width of the belt is along the y-axis. The particle is given a velocity v0 equal to 4 meters per second. Isn't it? Yes, 4 meters per second. The belt has a velocity 3 meters per second, right? Has a velocity 3 meters per second. So at t equal to 0, this is what? Eventually, what would you expect? There is relative motion between the belt and the particle, and therefore friction would act, kinetic friction, which is approximately maximum static friction. The particle therefore would be acted upon by a frictional force, which is maximum static or kinetic, roughly maximum static, which is kinetic. And what would it want to do? It would want, see, it can't do anything about the velocity of the belt. It's powered by some other mechanism, so the velocity of the belt will remain intact at 3 meters per second. But the frictional force can alter the velocity of the particle, eventually what would you expect? The frictional force will keep acting in a manner, till such time the velocity of the particle also becomes 3 meters per second in the same direction as the belt, right? And then when there is no relative motion between the particle and the belt, friction would cease. This is what would have happened, right? So, first thing, I want to be able to know the frictional force acting on the particle. There is relative motion. So what's the frictional force acting on the particle? Approximately mu mg is the frictional force. Let me not bother about the direction. That's the magnitude of the frictional force, which is roughly kinetic. And therefore, the acceleration produced by kinetic friction would be Fk by m, which is mu g. That's the acceleration produced, whose intention, so this magnitude of the acceleration will not change with time. The magnitude of the acceleration will remain mu g till the time the particle and the belt acquire the same velocity as that of the belt, which is 3 meters per second along the x-axis, right? So one thing, the acceleration because of friction that is produced on the particle will have a magnitude mu g, which will not change in magnitude while the particle has relative motion with respect to the belt. Now, what is the initial direction of this acceleration? Initial direction of this frictional force. Hey, look, the particle has a velocity v0 like this, which is 4 meters per second. The belt has a velocity like this along the x-axis, which is 3 meters per second, right? Therefore, the relative velocity between the two is going to be what? Velocity of the particle minus the velocity of the belt. That will be the relative velocity. So, if the velocity of the belt is 3 meters per second to the right, negative of the velocity of the belt will be 3 meters per second to the left. And velocity of the particle minus the velocity of the belt. This is negative of the velocity of the belt. 3 meters per second to the left is negative of the velocity of the belt. The resultant of the velocity of the particle and negative of the velocity of the belt would be the relative velocity of the particle with respect to the belt. That means, realize this is the x-axis, this is the y-axis, and the velocity of the particle with respect to the belt will be the resultant of velocity of the particle, and negative of the velocity of the belt will give me the relative velocity of the particle with respect to the belt. And what's the relative velocity of the particle with respect to the belt at time t equal to 0? It's going to be root 4 square plus 3 square, right? This is going to be root 4 square plus 3 squared, which is 5 meters per second, Root 4 square plus 3 square, that's 5 meters per second. Okay. Now, that relative velocity, say, makes an angle theta with the horizontal. That means this relative velocity has a component 5 cos theta like this, has a component 5 sin theta like this. Now, what about the frictional force? Frictional force will act like this, opposite to relative velocity, right? Frictional force is opposed to relative velocity. So frictional force will act like this, Fk, mu mg will act like this. Therefore, acceleration, which is mu g, will be produced like this, opposing relative velocity. Now, so when I'm talking of relative velocity, this is not just the absolute acceleration of the particle, this is also the relative acceleration of the particle, because acceleration of the belt is 0. So whatever is the absolute acceleration of the particle is also the relative acceleration of the particle in the belt frame of reference. Now, in the belt frame of reference, relative velocity and relative acceleration, they are along the same line. So the relative velocity will not change direction. That means velocity of the particle with respect to the belt will not change direction, it will only change magnitude. So mu g will keep killing the magnitude of the relative velocity but will not change the direction of the relative velocity, right? And mu g will keep acting till such time that the relative velocity becomes 0. One more thing, since the relative velocity and relative acceleration are parallel or anti-parallel vectors, right? That means the direction of relative velocity is not changing, and therefore the particle in a belt frame of reference will move along a straight line. That means the motion of the particle in the path of the particle in the belt frame of reference is going to be a straight line. And it's going to be the straight line which is the initial direction of the relative velocity, which is opposed by kinetic friction, which is producing retardation mu g to keep killing relative velocity by and by, right? Now, mu is given to be 0.5, so mu g is like 5 meters per second squared. If I take g as 10, mu as 0.5, so this is 5 meters per second squared is retardation produced. Initial, so what we have very clearly is, this is x-axis, this is the y direction, this is the x direction, and obviously as you can see from this figure, cos theta is going to be 3 by 5, sine theta is going to be 4 by 5, and so on and so forth, right? So theta is known to us, 4 by 5, 3 by 5, and so on and so forth. Now, eventually, the relative velocity vector is like this, as you can see, vrel is 5 meters per second like this, making an angle theta with the horizontal, and it's subject to a retardation which is 5 meters per second square, right? The particle with respect to the belt will keep moving in this direction because relative acceleration and relative velocity are along the same line. So eventually the relative velocity will become, so this is time t equal to 0. Eventually the relative velocity will become 0. Eventually the relative velocity will become 0. So I start with relative velocity equal to 5 meters per second. Final relative velocity is 0 plus a, which is minus 5 into t. T is the time taken for the let's say t naught seconds is the time it takes for the relative velocity to become 0. So that gives me t naught equal to 1 second. That means 1 second from the point of launch, the relative velocity will become 0. And when the relative velocity becomes 0, what happens to the particle? The particle will move. The particle will have a velocity synonymous with the velocity of the belt. The velocity of the particle in the ground frame will be the same as the velocity of the belt in the ground frame, which is 3 meters per second along the x-axis. So that happens after 1 second. That happens after 1 second. Because the relative velocity becomes 0, the velocity of the particle and the velocity of the belt become the same. Velocity of the belt remains 3 meters per second all the time. Now the velocity of the particle also becomes 3 meters per second at t equal to 1 second. Now what happens? Now what happens is, realize that while the particle is moving, what happens to its relative velocity vector? So first of all, realize that the initial relative velocity vector is like 5 cos theta horizontally leftwards and 5 sine theta upwards, right? And the net is 5 meters per second like this, right? Relative velocity t seconds later, the relative velocity is vrel. So vrel t seconds later would be 5 minus initial relative velocity, which is 5 minus at, 5 into t, which is like 5 into 1 minus t is the relative velocity, and it's along this line only, making an angle theta with the horizontal, leftward horizontal as shown. So that's the relative velocity in magnitude t seconds later. Initial relative velocity, which is 5 seconds, minus at. A is 5 meters per second square, right? Now, having said this, how do I write the relative velocity vector? The relative velocity vector is going to be 5 into 1 minus t cos theta component, right? Relative velocity will be like this. T seconds later, relative velocity becomes this, which is at an instant of time t. It makes an angle theta with the horizontal, leftward horizontal. This is the negative x-axis. So vrel cos theta in the minus I cap direction and vrel sine theta in the plus j cap direction. So 5 into minus 1 minus t cos theta is the component leftwards, right? vrel is 5 into 1 minus t cos theta along the minus I cap direction, and along the vertical direction, that means along the y-axis, it becomes vrel, which is 5 into 1 minus t sine theta j cap. right, in the vertical direction, this is what happens. So that's the velocity vector in the belt frame of reference t seconds later, yes or no, right? Now, evidently, what is the displacement of the particle in this direction in t seconds? Let's look at that. Let me remove the clutter from here. What's the displacement of the particle with respect to the belt t seconds later? With respect to the belt t seconds later, this is the y direction. In the belt frame of reference t seconds later, this is initial velocity, relative velocity is 5 meters per second, and this acceleration in the belt frame of reference is 5 meters per second square, right? So would you not want to believe that after a while, after 1 second, the relative velocity becomes 0, which we have computed? Relative velocity becomes 0, right? The particle in the belt frame of reference comes to rest. And this angle is theta, as we've already seen. This is theta, where cos theta, as witnessed earlier, was 3 by 5, sin theta was 4 by 5, right? We have seen this. The particle in the belt frame of reference continues to move in this direction, right? Now, what is this length, OP, that the particle covers? OP, as you can see, is going to be initial VR squared by 2A, right? VREL squared, which is initial VREL squared, which is 5 squared, divided by twice of acceleration, which is 10, right? So, which is like 2.5 meters. OP is 2.5 meters. And therefore, what is the vertical displacement along the width of the belt? This, which is like 2.5, this is theta, so this is like 2.5 sin theta. 2.5 sin theta? Yes or no? 2.5 sin theta means 2.5 into sin theta, which is 4 by 5. 0.5 into 4, which is 2 meters, right? That means when the particle comes to rest with respect to the belt, its displacement in the y direction is 2 meters. This displacement is 2 meters. This displacement is 2 meters. That is what happens to the particle. Now, if this displacement is 2 meters, that means the width of the belt, in order that the particle does not come out of the belt, the width of the belt has to be greater than or equal to 2 meters, right? So, width of the belt obviously has to be greater than or equal to 2 meters. So, what is the minimum width of the belt? The minimum width of the belt, so that the particle does not fall off the belt, is 2 meters. Is 2 meters. Yes or no? Do you all understand this? Now, this is not the end of the journey. The last part of the problem. Now we want to look at the speed of the particle in the ground frame of reference. This is the relative velocity with respect to the belt, which we have seen earlier. What is the velocity of the belt? The velocity of the belt is, as you can see, is 3 along the x-axis is 3 I cap. What's the velocity of the particle in the ground frame? It's going to be the relative velocity plus the velocity of the observer, which is reporting this relative velocity, which is the belt, right? So, what is that going to be? So, VREL, again cos theta I can plug in as 3 by 5. Right, cos theta is 3 by 5, so if I plug in cos theta as 3 by 5, this will become 3 into 1 minus t. And sin theta is 4 by 5, so this will become like a plus 4, because into j cap. I'm sorry if I have, manipulating things right here. So VREL is 3 into 1 minus t minus I cap plus 4 into 1 minus t j cap. That's the relative velocity as a function of time. Right, so which is like 3 into minus 3 into 1 minus t I cap plus 4 into 1 minus t j cap plus velocity of the belt, which is like 3I cap, right? That's the velocity of the particle in the ground frame as a function of time. Now you can see minus 3I cap will cancel with plus 3I cap. This is going to become, so velocity in the ground frame, if you simplify, what is it going to be? 3t I cap, and then 4 into 1 minus t j cap. This is what happens, right? And again, as you can see, at t equal to 1 second, the velocity in the ground frame becomes 3 meters per second along the x-axis, which is the velocity of the belt itself. So eventually, at t equal to 1 second, when relative motion ceases, the velocity of the particle and the belt will become the same. Friction will then go to rest. It will not act unnecessarily, right? Because relative motion would have ceased at t equal to 1 second. So all of this is t equal to till t equal to 1 second. T equal to 1 second onwards, the velocity of the particle remains the same as the velocity of the belt, which is 1 meter per second. Now, I want to find the minimum speed. So v square g, square of the speed as you can see would be like a 9t squared plus 16 into 1 minus t whole square. That's the square of the speed. If I take the magnitude of this vector, that's 9t squared plus 16 into 1 minus t whole squared is the square of vg, right? Now I want to find very clearly at different times I have different values of vg. I want to find the smallest vg, smallest speed in the ground frame by the time relative motion ceases, right? So now some mathematics. How do I do this? All right, so I want to find vg square minimum, and therefore vg minimum. For different t's, I'll have different vg's. Of course, this is all the way from t equal to 0 to t equal to 1 second, because after that, nothing that I've said will be relevant, right? So vg squared, as you can see, is like 9 plus 16, 25t squared. And then I have minus 32t. Then I have minus 32t plus 16. I hope all of you understand this. 16t squared plus 9t squared, 25t squared, then the middle term of this minus 32t plus 16. Or I can write this as a quadratic in t. I want to find vg minimum. So 25t squared minus 32t plus 16 minus vg squared is 0. For t to be real, discriminant of this quadratic has to be greater than or equal to 0. Or we have 32 squared minus 4 into 25 into 16 minus vg squared has to be greater than or equal to 0. Or we have 16 minus vg squared into 100. This is 100, right? 4 into 25, that is less than or equal to 32 squared. 32 squared is 1024. Or 16 minus vg squared is less than or equal to 10.24. Or vg squared has to be less than or greater than or equal to 16 minus 10.64 is 5.76. Or vg has to be greater than or equal to 2.4 meters per second. That means the minimum speed of the particle by the time it comes to rest in the belt frame of reference, relative motion ceases, is 2.4 meters per second. So the minimum speed of the particle in the ground frame of reference is going to be 2.4 meters per second. Yes or no? So this again is an interesting problem, but one thing that I want to share with you is, this is the velocity in the ground frame. And if I now want to find the path of the particle in the ground frame, then I look at the velocity in the ground frame. Look, this is like velocity, this is the velocity in the x direction, which is rate of change of x with time. dx dt is 3t, and dy dt, velocity in the y direction, as you can see, is 4 into 1 minus t. Right? Obviously at t equal to 0, the particle starts from the origin, x is 0 and y is 0. Right? And then I can obtain x as a function of time. X as a function of time in the ground frame is 3t squared by 2. Right? Y is going to be 4t minus 4t squared, 2t squared, 4t minus 2t squared, and I can eliminate t from these considerations. I mean, in the sense, what I could have done is I could have just said y plus 2t squared whole squared is 16t squared, and y squared plus 4yt squared plus 4t to power 4 is 16t squared. Now t squared and t to the power 4 can be obtained from this, because t squared is 2x by 3. So t to the power 4 is going to be 4x squared by 9. So replace t squared and t to the power 4, t squared and t to the power 4 by 2x by 3 and 4x squared by 9, and you get the trajectory of the particle. You get the trajectory of the particle in the ground frame, and you could check that it'll turn out to be a parabola. It'll turn out to be a parabola. The trajectory in the ground frame will turn out to be a parabola. The trajectory in the belt frame is going to be a straight line. This certainly makes sense. This problem, I would think, would be like loads of relevant pertinent things pertaining to friction and motion and Newton's laws, all packaged in one. I really found it very interesting, very exciting, and I hope you will find it interesting and exciting too. Thank you so much. This situation on friction is about a plank which is moving to the right with a velocity of 2 meters per second, and there is a block that rests on the plank which is also moving to the right with a velocity of 2 meters per second. And the coefficient of friction, static as well as kinetic, is given to be 0.1 between the block and the plank. Now what happens is, this plank starts to decelerate uniformly. That means uniform deceleration, and it eventually stops in 0.5 seconds, right? If it stops in 0.5 seconds, what we need to find out the distance traversed by the block on the plank. That means distance traversed by the block with respect to the plank, that is upon the block, by the time the plank comes to rest. This is what we need to find, right? Now one thing, if the plank decelerates uniformly, that means its retardation A is going to be given by total change in velocity 2 minus 0 divided by 0.5 meters per second squared. That means 4 meters per second squared is its retardation, right? Ideally then friction would want to retard block B also, because it would want to maintain the block and the plank. It would want to maintain the block and the plank at the same velocity at all times. It would want to prevent relative motion. But what's the maximum possible retardation of the block? Maximum possible acceleration or retardation that friction can give to the block will always be mu g. Mu is given to be 0.1. So this is 1 meter per second squared. That means, hey, bad luck. It requires 4 meters per second squared as the retardation so that it can stay tuned with the plank, but it cannot have. Friction can go only to the tune of 1 meter per second squared, right? Maximum retardation that this can give is, because see, if the block has to retard, friction will act on it in this direction, right? And this friction would have to be less than or equal to mu mg, right? Mu mg. This friction is, so if it has a retardation a naught here, then F is ma naught leftwards, which cannot be less, cannot exceed mu mg. Therefore, a naught has to be less than or equal to mu g. That means the maximum retardation courtesy friction is mu g. That means it is not matching with 4 meters per second squared. That means, hey, it'll go ahead with the maximum it could. It requires 4 to keep pace with the plank, but it cannot have 4, so it has a leftward acceleration of 1 meter per second squared, right? Now, in one second, what is the, or rather, what's the distance covered by the plank by the time it comes to rest? Its initial velocity is v naught. So distance covered by the plank in the ground frame is going to be v naught squared divided by 2a. A is given to be found to be 4 meters per second squared. V naught squared, which is 4 divided by 2 into 4, which is 0.5 meters to the right. The plank would have moved 0.5 meters to the right, right? Now, in 1 second, how much distance would the block have moved? Distance moved by the block in the ground frame would be ut, 2 into t, u2 into t, t is 0.5 minus half of a, maximum a that it can have is 1 meter per second squared, a into t squared, t is 0.5 squared. 0.5 square. So which is like 1 minus half of 0.25. So 1 minus 0.125. 1/8, which is 7/8 of a meter. By the time the plank comes to rest, it would have covered ut minus half of a into t squared, right? But eventually this will also come to rest, right? Eventually this will also come to rest. So what's the total distance covered by the block by the time the block comes to rest? The total distance covered by the block by the time the block comes to rest is going to be 2 squared v squared by 2a. A is 1, which is 2 meters, right? So now, what is the, so in the ground frame, by the time the block comes to rest, the block would have traversed a distance 2 meters, right? What would have plank done? The plank would have covered a distance 0.5 meters. 0.5 meters. That means with respect to the plank, what is the distance covered by the block? With respect to the plank, the distance covered by the block, well, is in the ground frame 2 minus the distance covered by the plank, which is 0.5. So 1.5 meters is the distance covered by the block with respect to the plank by the time the block also comes to rest. The block will take a little while to come to rest. The plank would have come to rest earlier because the plank has a greater retardation, the block has a smaller retardation, and they are starting with the same velocity. So 1.5 meters would have been the distance covered by the block with respect to the plank when both come to rest, right? So distance covered by the plank, as you can see, is 0.5 meters. It stops there, right? But the distance covered by the block is going to be 2 meters when the block stops. So in the plank frame of reference, the distance covered by the block is going to be the distance covered in the ground frame by the block minus the distance covered in the ground frame by the plank, which is 0.5. So that makes it 1.5 meters. Yes or no? Thanks a lot. Bye.